If humanity disappeared tomorrow, what would people thousands of years in the future think when they found the remains of our world? They would see airports without airplanes, tunnels without trains, and skyscrapers without any record of who built them. They would have evidence but not context, and that is exactly the challenge we face when looking at the ancient world. We inherit the physical remains of civilizations, but rarely the full explanations behind them. A stone structure can survive for millennia while the ideas that created it vanish in a few generations. The result is a past filled with unanswered questions. Not because ancient people failed to leave clues, but because time removed the key needed to understand them. Every ancient mystery begins at that point, where evidence survives but meaning does not. Selka i Poshtme, hidden in the hills of eastern Albania overlooking the Shkumbin River Valley, contains a group of royal tombs that should not exist as they do. More than 2,200 years ago, builders carved monumental chambers directly into solid rock, created sophisticated architectural facades, and constructed burial complexes that continue to survive despite earthquakes, weathering, and centuries of abandonment. Yet the civilization responsible left behind almost no technical records. Today, archaeologists can measure the tombs with laser scanners and analyze the stone at microscopic levels, but some of the most important questions remain unanswered. The mystery was first brought to scholarly attention during archaeological investigations in the 20th century, although the site had been known locally for generations. Systematic excavations conducted between the 1960s and 1970s revealed a remarkable complex of Illyrian royal tombs dating primarily between the 4th and 3rd centuries BC. The discoveries immediately attracted attention because the architecture displayed a level of engineering and craftsmanship far beyond what many historians had previously associated with the Illyrian kingdoms of the Balkans. The first mystery concerns the construction itself. Selka i Poshtme contains several rock-cut tombs excavated directly into the mountainside. Unlike ordinary masonry structures, these chambers required workers to remove enormous quantities of stone while preserving the structural stability of the remaining rock. Modern mining engineers understand how difficult this process can be, as a single miscalculation can create fractures that spread through the rock mass and cause collapse. The builders somehow avoided this problem. Even today, many of the chambers remain structurally intact despite more than 20 centuries of natural stress. Archaeologists have identified carefully planned layouts, symmetrical designs, and architectural details that suggest the builders understood much more about rock behavior than previously assumed. The challenge becomes even more impressive when compared with other ancient civilizations. The rock-cut tombs of Petra in Jordan, the Lycian tombs of Turkey, and the royal tombs of Macedonia all required advanced stoneworking techniques. Selka i Poshtme belongs in this category of sophisticated engineering projects, yet the technical tradition behind it remains largely undocumented. The second mystery involves surveying technology. Before a single stone could be removed, the builders needed accurate measurements. The tomb facades feature balanced proportions, straight lines, aligned entrances, and carefully organized internal spaces. Such precision requires some form of surveying system. The problem is that no measuring instruments have been discovered. No engineering manuals survive, and no written explanations describe how the work was organized. Historians know that Greek and Macedonian engineers used ropes, plumb lines, sighting tools, and geometric techniques. It is possible that Illyrian builders employed similar methods. However, direct evidence remains scarce. This creates an intriguing question. Did the engineers of Selka i Poshtme develop their own surveying traditions, Or were they adapting knowledge imported from neighbouring cultures? The answer remains uncertain. The third mystery centres on labour organisation. Creating the tombs would have required a workforce far larger than a handful of craftsmen. Archaeologists estimate that thousands of hours of labour were necessary to excavate chambers, shape facades, transport debris, and finish decorative elements. Even with iron tools, cutting solid limestone is slow work. Experimental archaeology has demonstrated that removing a single cubic metre of hard rock using ancient hand tools can require dozens or even hundreds of labour hours depending on rock quality. Some portions of the Selka tombs contain volumes of removed stone measured in many tens of cubic metres. Questions naturally arise. Who organised this labour? How were workers supplied with food, water and tools? And how was technical knowledge transferred between generations? These questions remain largely unanswered because the administrative records that might explain the process have vanished. The fourth mystery concerns the disappearance of technology itself. The tombs reveal impressive capabilities. Their builders understood stone extraction, geometry, architectural planning, and project management. Yet much of this expertise appears to have disappeared from the historical record. This pattern occurs repeatedly throughout ancient history. The builders of the Great Pyramid created monuments whose construction methods are still debated. The engineers responsible for Roman concrete developed materials that survived millennia, while parts of their knowledge were forgotten. The creators of the Antikythera mechanism produced a machine centuries ahead of its time, while leaving almost no technical instructions. Selka Epochtmer belongs to the same category of historical enigmas. The structures remain, but the knowledge largely vanished. Perhaps the most fascinating mystery of all involves something invisible. The fifth mystery is the ventilation and humidity control system. At first glance, ventilation seems far less impressive than carving a tomb into a mountain. In reality, it may represent one of the most sophisticated aspects of the entire complex. Moisture is one of archaeology's greatest enemies. Water promotes biological growth, accelerates chemical weathering, damages pigments, weakens surfaces, and gradually destroys ancient structures. Modern museums invest millions of dollars controlling humidity because even small fluctuations can damage artifacts over time. Yet, some chambers at Selka Epochtmer have survived for more than 2,000 years with remarkable preservation. Why? Researchers have proposed several explanations, but no definitive answer exists. One possibility is geological selection. The builders may have deliberately chosen sections of limestone with lower permeability. Geological studies show that different limestone formations can vary dramatically in how they absorb and transmit water. Selecting the right rock could significantly reduce moisture infiltration. Another possibility involves chamber orientation. Ancient builders throughout history frequently considered airflow when designing enclosed spaces. Egyptian tomb architects, Roman engineers, and underground builders in Cappadocia all exploited natural air circulation patterns. Small differences in entrance placement can affect temperature stability and air exchange rates for centuries. Some researchers suspect the architects of Selka Epochtmer may have possessed similar practical knowledge. The tomb entrances appear positioned in ways that could influence airflow, while internal chamber dimensions may also have helped regulate temperature changes. Stable temperatures reduce condensation, which in turn reduces humidity-related damage. A third possibility concerns hidden microventilation. Even tiny cracks within limestone can function as natural air channels. Modern cave scientists have documented airflow systems operating through openings only millimeters wide. These invisible pathways can gradually exchange air while limiting direct exposure to rain and weather. Could the builders have recognized such geological features? There is no proof, yet the possibility remains intriguing. Comparisons with other ancient sites make the mystery even more interesting. The tombs of Egypt often suffered from humidity fluctuations once entrances were opened. Many painted chambers in Europe experienced deterioration after modern excavation altered their internal climate. At Lascaux Cave in France, changes in air circulation created preservation challenges so serious that public access had to be restricted. Selka-e-Postme presents a different puzzle. The chambers appear to have maintained relatively stable conditions for centuries without any known mechanical systems. Whether this resulted from deliberate engineering, geological luck, or a combination of both remains unknown. The sixth mystery involves tool technology. The stone surfaces preserve evidence of cutting, shaping, and finishing, and every mark represents a tool that once existed. Yet the tools themselves are largely absent. How often were iron chisels replaced? How were cutting edges sharpened? What metallurgical techniques produced durable tools capable of sustained excavation? Without answers to these questions, archaeologists possess the results of the work but not the full technological process behind it. The final mystery is the society that created the tombs. Large engineering projects do not emerge from isolated individuals. They require political authority, economic resources, specialized knowledge, and social organization. Selka-e-Postme suggests the existence of a powerful and technically capable elite within the Illyrian world. However, the broader system that supported these achievements remains poorly understood. The engineers disappeared, the craftsmen disappeared, and the rulers disappeared. Only the stone survived. What do you think is the greatest mystery of Selka-e-Postme? The lost engineering techniques, the possible humidity control system, or the vanished knowledge of the Illyrian builders? Share your thoughts in the comments below. Khamir Blur, overlooking the Arafat plain near modern Yerevan, Armenia, preserves one of the greatest unsolved engineering mysteries of the ancient world. This fortress was capable of storing enough food and wine to sustain an entire regional power, yet the technology behind its massive storage system disappeared more than 2,600 years ago, leaving historians and archaeologists with questions that remain unanswered to this day. The site was identified in 1936 by Armenian archaeologist Boris Piotrowski, after local farmers repeatedly uncovered ancient artifacts in the area. Subsequent excavations revealed the remains of Teishabaini, a major fortress city of the Kingdom of Urartu that was destroyed around 585 BC in a catastrophic fire, preserving a remarkable snapshot of life in the ancient kingdom. Ancient cities are often difficult to understand because centuries of rebuilding tend to erase evidence of everyday life. Khamir Blur is different. When Teishabaini was destroyed, an intense fire caused roofs to collapse, sealed storage rooms, and preserved thousands of objects beneath layers of debris. As a result, archaeologists uncovered weapons, tools, textiles, wooden objects, agricultural products, animal remains, administrative tablets, and enormous storage facilities. The scale of preservation has often been compared to Pompeii, although Teishabaini predates Pompeii's destruction by more than 6 centuries. The fortress occupied a strategic hill overlooking major trade and military routes. Built during the reign of King Rusa II of Urartu in the 7th century BC, it served as a military, economic, and administrative centre on the northern frontier of one of the most powerful kingdoms in the Near East. Yet among all the discoveries made at the site, one mystery stands above the rest. The most astonishing discovery at Khamir Blur was not its walls or weapons, but its storage infrastructure. Excavations revealed dozens of storage rooms containing enormous ceramic jars known as caresses. Some stood nearly 2 meters tall, and many were partially buried into the floor to improve stability. Together, these vessels formed one of the largest known storage complexes in the ancient Near East. Researchers estimate that some individual jars could hold between 800 and 1,200 litres. Entire rooms contained rows of these vessels, arranged with remarkable precision, and the total storage capacity of the fortress may have exceeded hundreds of thousands of litres of grain, wine, oil, and other agricultural products. To understand the scale, one can compare it to a modern supermarket warehouse. Although Teishabaini lacked forklifts, refrigeration systems, and steel shelving, its storage facilities performed many of the same functions, including long-term preservation, inventory control, distribution management, and maintenance of emergency reserves. The engineering challenge involved was extraordinary. Grain naturally attracts insects, wine deteriorates when exposed to oxygen, and stored food is vulnerable to humidity fluctuations, mold growth, rodents, and temperature changes. Modern food storage relies on climate control systems, chemical treatments, sealed containers, and continuous monitoring. The Urartians possessed none of these technologies, yet archaeological evidence suggests that their stored supplies remained usable for extended periods. How they achieved this remains uncertain. One theory focuses on architectural design. Many storage rooms were built with thick walls that reduced temperature fluctuations, while the large ceramic vessels themselves may have acted as thermal stabilizers. Similar principles are still used today in underground wine cellars where stable temperatures improve preservation. Another theory involves airflow engineering. Some researchers believe that the arrangement of corridors, rooms, and ventilation openings may have created passive cooling effects. Comparable concepts later appeared in Persian wind catchers and Roman granaries, designed to reduce moisture accumulation. However, no surviving written document explains the system. The mystery becomes even deeper when examining administration. Thousands of storage containers required constant monitoring, and officials needed methods to record quantities, track deliveries, prevent spoilage, and coordinate redistribution. Clay tablets discovered at Urartian sites demonstrate sophisticated record-keeping, but the complete logistical system remains unknown. Questions such as how many workers managed the warehouses, how often supplies were rotated, how losses were measured, and how harvests were allocated remain largely unanswered. Even modern archaeologists equipped with laboratory analysis, digital reconstruction software, and climate modelling cannot fully explain how such a large storage network operated so efficiently. Another remarkable mystery concerns manufacturing. Excavations recovered thousands of bronze and iron objects, including swords, spears, arrowheads, shields, helmets, and armor components. Many of these artifacts exhibit remarkable consistency in both dimensions and quality, suggesting organized production rather than individual craftsmanship. Producing identical military equipment on a large scale requires quality control, specialized workshops, trained labor, and standardized measurements. Comparisons with contemporary civilizations are revealing. Assyria, Urartu's great rival, maintained state-controlled industries that supplied imperial armies. Evidence from Khmer Blur suggests that Urartu may have developed similar industrial capabilities, yet almost no technical documentation survives. Archaeologists can analyze the finished products, but the manufacturing processes themselves remain largely invisible. Khmer Blur stands within a tectonically active region. Modern Armenia experiences frequent seismic activity due to the collision of the Arabian and Eurasian tectonic plates. The fortress demonstrates a fascinating combination of materials, with massive basalt foundations supporting upper structures constructed from mud brick. At first glance, this arrangement appears simple, but in reality it may represent a sophisticated engineering solution. Stone provides strength, while mud brick reduces weight. Lower structural mass generally decreases earthquake damage because less force is generated during seismic movement. This principle forms part of modern earthquake engineering. Whether Eurasian builders discovered the same concept through centuries of observation remains unknown. No surviving text provides an answer, yet the recurring use of this construction method across multiple Eurasian sites suggests deliberate design rather than coincidence. Large-scale storage and manufacturing require organization, and Khmer Bleu reveals evidence of a surprisingly complex bureaucracy. Administrative seals, inscriptions, tablets, and official storage facilities all point towards centralized control. Some scholars compare Urartu's administration to a smaller version of the Assyrian imperial system. The fortress appears to have functioned as a regional hub where taxes, agricultural production, military supplies, and trade goods were collected and redistributed. Managing such a system without paper, computers, or rapid communication posed enormous challenges, yet somehow it worked. The administrative knowledge that coordinated this machine disappeared almost completely after the collapse of the kingdom, leaving only fragments of evidence behind. Around 585 BC, Taishabini was destroyed in a sudden and violent event. Archaeologists discovered evidence of intense fire throughout the site. Collapsed roofs buried storage rooms, weapons remained where they had been used, and some human remains suggest that inhabitants attempted to flee during the attack. The identity of the attackers remains uncertain. The leading candidates include Scythian raiders, Median forces, or other regional enemies taking advantage of Urartu's weakening power. No definitive answer exists. The attackers vanished into history, leaving behind only the destruction layer. Ironically, the catastrophe that ended the city also preserved it. Without the fire, much of the evidence archaeologists study today might never have survived. What do you think was Khmer Bleu's greatest achievement? The massive storage system, the advanced metallurgy, or the lost knowledge that allowed an ancient kingdom to manage an entire fortress city without modern technology? Share your thoughts in the comments below. Knockrow Passage Tomb is a prehistoric monument in County Kilkenny, Ireland, built around 3200–3000 BC. More than 5,000 years ago, long before written records appeared in Ireland, its builders created one of the most remarkable astronomical structures in Neolithic Europe. Unlike most passage tombs, Knockrow contains two separate passages aligned with two different solar events. Every winter solstice, sunlight enters one passage at sunrise and the other at sunset. The monument still performs this function today. The mystery is simple but profound. How did Stone Age communities achieve such precision without mathematics, instruments, or written knowledge? The site remained largely hidden beneath vegetation and soil for centuries. Modern archaeological investigations during the 20th century revealed a complex monument consisting of a central mound, two stone-lined passages, burial chambers, and numerous decorated stones. Excavations demonstrated that Knockrow belonged to the same broader tradition as Newgrange and Noath, yet it possessed unique characteristics that immediately attracted scientific attention. The greatest mystery of Knockrow concerns astronomical alignment. The winter solstice occurs when the sun reaches its southernmost position in the sky, producing the shortest day of the year. At Knockrow, both passages appear deliberately oriented toward this event. One captures the first light of the solstice sunrise. The other captures the final light of the solstice sunset. This arrangement is extraordinarily rare. Modern engineers can calculate solar positions using computers, satellite data, and precise coordinates. The builders of Knockrow possessed none of these tools, yet archaeological surveys indicate that the alignments were intentional rather than accidental. To achieve this result, Neolithic observers would have needed to monitor the horizon for many years, perhaps generations, recording where the sun rose and set throughout the annual cycle. The challenge becomes clearer when compared with modern measurements. The position of the winter solstice sunrise changes very little near the turning point of the year. Small observational errors can produce significant deviations in alignment. A mistake of only a few degrees would prevent sunlight from reaching the intended chamber. Nevertheless, the passages function successfully for millennia. Researchers have proposed several explanations. One theory suggests that specialized observers tracked solar movements year after year using wooden markers placed on distant horizons. Another proposes that communities inherited accumulated observations through oral traditions. A more controversial hypothesis argues that Neolithic societies possessed practical surveying techniques far more sophisticated than traditionally assumed. The problem extends beyond astronomy. Builders first had to identify the exact solstice position, then transfer that information into a construction plan, then maintain accuracy throughout the building process. Every stone placement affected the final alignment. This required a level of planning comparable to complex engineering projects. The comparison with Newgrange is revealing. Newgrange, built around the same period, is famous for its winter solstice illumination event, yet Newgrange focuses primarily on sunrise. Knockrow appears to incorporate both sunrise and sunset into a single architectural system. This dual alignment raises questions about purpose. Why create two passages? Why invest additional labour and resources? What symbolic meaning justified the extra complexity? Some archaeologists believe the monument functioned as a ceremonial calendar. Agricultural societies depended on seasonal timing. Knowing precisely when winter reached its turning point could help organise rituals and mark the transition toward longer days. Others argue the alignments carried religious significance rather than practical value. The absence of written records prevents definitive conclusions. A second mystery involves the engineering of the monument itself. Passage tombs require the transportation of enormous quantities of stone. Individual blocks weighing several tons had to be quarried, moved, positioned and stabilized without metal tools, wheels, or draft animals. Experimental archaeology has demonstrated that such transport is possible using wooden rollers, sledges, ropes, and coordinated labour. However, no direct evidence reveals which methods were actually employed at Knockrow. The logistical challenge becomes even more impressive when viewed in a broader European context. During the same period, communities across Atlantic Europe were constructing megalithic monuments, including passage tombs in Ireland, chambered cairns in Scotland, and stone alignments in Brittany. Knockrow forms part of this wider phenomenon, yet researchers still debate how technological knowledge spread across such vast distances. Did communities exchange ideas through long-distance contacts, or did similar solutions emerge independently? The decorated stones of Knockrow present another enduring puzzle. Archaeologists documented numerous examples of megalithic art carved into stone surfaces. Spirals, concentric circles, zigzags, arcs, and geometric motifs appear throughout the monument. These designs resemble carvings found at Newgrange and Noath, suggesting a shared symbolic tradition. Yet no universally accepted interpretation exists. Some scholars see representations of solar cycles, lunar movements, or seasonal change. Others view them as religious symbols connected to beliefs about death and the afterlife. A few researchers have even suggested that the patterns may encode information, functioning as a form of symbolic communication. The difficulty lies in the lack of context. Unlike Egyptian hieroglyphs or Mesopotamian cuneiform, these symbols remain undeciphered. Their creators left no explanations. Modern researchers can analyze the carvings with lasers, digital imaging, and microscopic techniques, but the meanings behind the patterns remain elusive. Another mystery concerns surveying technology. Constructing aligned passages required more than astronomical observations. Builders also needed methods for maintaining direction during excavation and stone placement. Modern surveyors use compasses, levels, theodolites, GPS receivers, and laser instruments. Neolithic builders relied entirely on simple tools and human observation. Experimental studies suggest that surprisingly accurate alignments can be achieved using wooden stakes, sighting lines, and repeated measurements. However, reproducing the exact precision observed at monuments like Knockrow remains challenging. The monument implies a practical understanding of geometry long before formal mathematics appeared in Europe. The monument also raises questions about social organization. Large-scale construction projects require labor coordination, food production, planning, and leadership. Hundreds of people may have participated in quarrying, transporting materials, preparing the site, and constructing the mound. Such activities imply a society capable of organizing collective efforts on a significant scale. This challenges older assumptions about Neolithic communities. Rather than isolated farming groups with limited technical knowledge, sites like Knockrow suggest organized societies capable of managing complex projects over extended periods. Yet archaeologists still debate how authority functioned within these communities. Were they led by chiefs, religious specialists, councils, or cooperative networks? Perhaps the most fascinating mystery is the disappearance of the knowledge itself. The builders of Knockrow understood astronomy, surveying, monument construction, logistics, and symbolic design. They created a structure that still demonstrates its intended function more than 5 millennia later. Yet they left behind no manuals, no calculations, no blueprints, and no written explanations. What do you think was the greatest achievement of Knockrow Passage Tomb? The precise winter solstice alignments, the engineering required to build it, or the lost knowledge that made it all possible? Share your thoughts in the comments below. Otzenhausen ring wall, known as the Hunnen Ring, stands in the hills of Saarland, western Germany. More than 2,000 years ago, Iron Age engineers built one of the largest fortifications in prehistoric Europe. Today, its massive stone walls still rise from the forest, but the knowledge that created them has largely vanished. The site was known locally for centuries, but systematic archaeological investigations began during the 19th century and expanded throughout the 20th century. Excavations revealed that the fortress was constructed by the Celtic Treveri tribe during the late Iron Age, around the 1st century BC. What researchers uncovered was not a simple hill fort, but an engineering project of astonishing scale. The most extraordinary mystery of Otzenhausen is its colossal defensive wall. The fortress encloses approximately 18 hectares and is surrounded by walls extending more than 2.5 kilometers in length. In some places, the ramparts remain nearly 10 meters high and over 10 meters thick. Archaeologists estimate that hundreds of thousands of tons of stone were used during construction. At first glance, the walls appear simple, but closer examination reveals something far more sophisticated. The builders did not rely on mortar. They created enormous structures by combining carefully placed stone blocks with an internal timber framework. The resulting design belongs to a class of Celtic engineering known as the Murus Gallicus, described by Julius Caesar during his campaigns in Gaul. Caesar wrote that these walls possessed remarkable resistance to both fire and battering attacks, and modern engineering studies suggest he may have been correct. Unlike rigid masonry walls that can crack under impact, the combination of timber and stone distributed force throughout the structure. The wooden beams acted like shock absorbers hidden inside the wall. What remains mysterious is how Iron Age builders achieved such precision. constructing a wall more than 2.5 kilometers long required maintaining alignment across rugged terrain while ensuring structural stability. Modern engineers would use surveying equipment, mathematical calculations, and detailed plans. The Celts left no blueprints, no engineering manuals, and no written explanations. Yet the walls survived for more than 2 millennia. Experimental archaeology has demonstrated that recreating even small sections of Murus Gallicus construction requires careful planning and extensive labour. Scaling that process to the dimensions of Otzenhausen suggests a level of technical expertise far beyond traditional assumptions about Iron Age Europe. The Great Pyramid required approximately 2.3 million stone blocks, and the Romans built concrete fortifications throughout their empire. Otzenhausen represents a different engineering tradition altogether. A massive defensive system constructed largely from local resources without mortar, concrete, cranes, or written technical documentation. Exactly how the builders designed and coordinated such a project remains unknown. Before construction could begin, someone had to decide where the walls would go. This problem sounds simple until the scale becomes apparent. The perimeter stretches across hills, slopes, ridges, and uneven ground. Every segment had to connect to the next while maintaining defensive effectiveness. The walls needed to maximize visibility, control access routes, and exploit natural terrain. Modern surveyors would use GPS systems, laser scanners, drones, and topographic maps. The Treveri had none of these. Yet aerial surveys show that the fortifications were positioned with remarkable strategic efficiency. Defensive lines consistently occupy advantageous terrain while minimizing vulnerable approaches. How did Iron Age surveyors measure distances across forests and hills? How did they maintain alignment over kilometers of construction? No definitive answer exists. Some researchers believe specialized surveyors may have used wooden sighting devices, measuring ropes and accumulated practical knowledge passed through generations. The problem is that no direct evidence survives. The walls remain, but the methods disappeared. The fortress required an enormous volume of material. Stone had to be extracted, transported uphill, sorted and placed into position. Timber had to be harvested, shaped and integrated into the structure. Iron nails and metal components had to be manufactured. The logistics alone are staggering. Even if individual stones weighed only a few hundred kilograms, the total volume of material likely reached hundreds of thousands of tons. Transporting such quantities without modern vehicles represents one of the site's greatest mysteries. Comparisons with other ancient projects reveal the challenge. The builders of Stonehenge transported bluestones across more than 200 kilometers. The engineers of Easter Island moved multi-ton Moai statues. At Otzenhausen, the challenge was not moving a few monumental objects, but sustaining a continuous flow of construction material on an industrial scale. Archaeologists still debate the exact transportation methods. Were wooden rollers used? Were sledges pulled by oxen? Did temporary roads exist? Evidence remains incomplete. One of the most overlooked mysteries involves wood. The internal framework of the Murus Gallicus depended heavily on timber. Thousands of beams were integrated into the walls. Wood is vulnerable to decay, insects, moisture, and structural failure. Yet enough survive for archaeologists to reconstruct portions of the design more than 2,000 years later. This raises difficult questions. Did the builders select specific tree species for particular structural roles? Did they understand long-term load distribution? Did they possess preservation techniques that are no longer recognized? Modern structural engineers carefully calculate how wood behaves under stress, yet the Treveri achieved durable results without modern materials science. much of that knowledge vanished before it could be recorded. Engineering alone could not create Otzenhausen. The project required labour management on a massive scale. Workers had to quarry stone, harvest timber, forge tools, transport materials, construct walls, maintain food supplies and coordinate schedules. This implies sophisticated administration. Historians estimate that large prehistoric construction projects often required thousands of workers operating over extended periods. Such efforts demand planning, leadership, and resource control. Yet almost nothing is known about the organizational system behind Otzenhausen. Who directed construction? How was labor divided? How long did the project take? The archaeological evidence provides only fragments. The human system that made the fortress possible remains largely invisible. Another mystery concerns the site's true purpose. Traditional interpretations describe Otzenhausen as a defensive stronghold, but excavations suggest something more complex. Archaeologists have identified evidence of habitation, storage, craft production, and economic activity within the enclosure. This indicates that the site may have functioned not only as a military fortress, but also as a political centre, trading hub, refuge, and symbol of regional power. The scale supports this possibility. Few communities invest such enormous resources solely for defence. Some researchers believe the fortress represented a central place within Treveri society, combining military, economic, and ceremonial functions. The exact balance remains uncertain. What do you think was the most impressive achievement of Otzenhausen Ringwall? The giant mortarless walls, the lost surveying knowledge, or the organisation required to build one of Europe's largest Celtic fortresses? Share your thoughts in the comments below. Oppidum Saint-Vincent stands above the Rhône Valley in southern France, where the ruins of an Iron Age hilltop settlement preserve evidence of engineering knowledge that disappeared more than 2,000 years ago. The site was identified through archaeological surveys and excavations conducted throughout the 20th century, revealing fortifications, habitation areas, imported goods, and evidence of metalworking activity dating from the late Iron Age through the Roman period. At first glance, Oppidum Saint-Vincent appears to be another Celtic hill fort. Yet archaeologists quickly realised that the settlement represented something much more complex. Built on elevated terrain overlooking important routes connecting inland Gaul with the Mediterranean world, the site occupied a strategically valuable position. The hilltop location provided visibility across surrounding landscapes, but it also created enormous engineering challenges. Every stone, timber beam, tool and food supply had to be transported uphill. Defensive walls had to remain stable on uneven slopes. Water had to be collected and stored despite the absence of major springs directly within the settlement. These problems required practical engineering solutions. The mystery is that the people who developed those solutions left almost no written explanations behind. Unlike Roman engineers, who documented aspects of construction and military planning, the Celtic communities of southern Gaul transmitted knowledge primarily through oral traditions. As a result, the structures survive while the technical manuals are gone. One of the first puzzles involves the placement of the settlement itself. Modern topographic analysis demonstrates that the builders selected a location providing exceptional control over movement through the region. From the hilltop, large sections of the surrounding landscape become visible. Important communication and trade routes could be monitored from a single defensive position. This raises an important question. How did Iron Age surveyors identify such locations without maps, aerial views, satellites, or modern instruments? Archaeologists know ancient builders throughout Europe possessed practical surveying skills. The creators of the massive earthworks at Maiden Castle in Britain, The engineers of Manching in Germany and the planners of Bibracte in central France all demonstrated sophisticated understanding of terrain. Oppidum Saint-Vincent belongs to the same tradition. Researchers suspect that generations of accumulated local knowledge allowed ancient surveyors to analyze sightlines, elevations, slopes, and access routes with remarkable precision. Yet exactly how those calculations were performed remains unknown. The fortifications themselves present another technological puzzle. Excavations indicate that the settlement was protected by substantial defensive structures that evolved over time. Rather than constructing a single wall, the inhabitants repeatedly modified and reinforced their defenses as military requirements changed. This pattern demonstrates long-term planning. Building defensive systems requires understanding structural stability, labor organization, material properties, and terrain interaction. Even today, military engineers must consider similar variables when designing fortifications. The challenge becomes more impressive when compared with contemporary settlements. Many Iron Age communities constructed simple earthworks. Oppidum Saint-Vincent appears to have employed more complex combinations of stone, earth, and timber. Such hybrid construction techniques often absorb impact more effectively than stone alone. Yet archaeologists still debate the exact construction sequence. Were the walls built according to standardized plans? Did specialized engineers oversee projects? How was technical knowledge transmitted between generations? The evidence remains incomplete. Water may have been the settlement's greatest engineering challenge. Every hilltop community faces the same problem. High ground offers security but limits access to reliable water supplies. During sieges, water shortages can become catastrophic. The long occupation of Oppidum Saint-Vincent suggests that its inhabitants successfully solved this problem. The question is how? Some researchers believe rainwater collection systems may have existed. Others suggest underground cisterns, storage basins, or engineered drainage networks. Similar technologies are known from Iron Age sites elsewhere in Europe. At Bibracte, archaeologists discovered sophisticated hydraulic features. At several Mediterranean settlements, water storage systems enabled populations to survive extended dry periods. If comparable systems existed at Saint-Vincent, much of the evidence may have been destroyed by erosion, later construction, or centuries of abandonment. As a result, the hydraulic infrastructure remains one of the site's least understood technologies. The most fascinating technological mystery of Oppidum Saint-Vincent concerns metal production. Archaeological evidence suggests that metalworking activities occurred within or near the settlement. While the scale of production remains debated, even small-scale metallurgy required extraordinary technical expertise. Modern experiments demonstrate that producing usable iron is far more difficult than most people imagine. Iron ore does not simply become metal when heated. Ancient metallurgists had to identify suitable ores, construct furnaces, control airflow, regulate fuel consumption, and maintain temperatures exceeding 1,100 degrees Celsius. Small mistakes could ruin an entire batch. The remarkable fact is that Iron Age craftsmen achieved these results without thermometers, chemistry textbooks, pressure gauges, or scientific laboratories. They relied entirely on observation and experience. Experimental archaeology has shown that furnace operators could estimate temperatures by examining flame color, spark behavior, airflow patterns, and the appearance of heated metal. Such skills required years of practice. This creates a profound mystery. How was this knowledge preserved? A successful ironworking tradition depends on countless technical details. Furnace dimensions must be correct. Charcoal quality must remain consistent. Airflow must be carefully managed. Ore impurities must be recognized and compensated for. Modern metallurgical engineers learn these principles through formal education. Iron Age craftsmen learned them without written manuals. The comparison with other ancient cultures is revealing. The Hittites developed advanced ironworking traditions in Anatolia. Celtic communities across Gaul became renowned for metal craftsmanship. Roman armies later depended heavily on iron tools and weapons. In every case, specialized metallurgical knowledge formed the foundation of economic and military power. Yet very little documentation survives. Oppidum Saint-Vincent may preserve evidence of one small piece of this vanished technological world. Some archaeologists argue that Celtic metalworkers possessed highly standardized production methods. Others believe expertise remained concentrated among small groups of specialist craftsmen. Neither theory fully explains how technical consistency was maintained across generations. The problem resembles other great technological mysteries of antiquity. The builders of Roman concrete produced materials that survived millennia. The creators of the Antikythera mechanism constructed an ancient analog computer of astonishing complexity. The engineers of the Great Pyramid completed one of history's most ambitious construction projects. In each case, the products survive while much of the underlying technical knowledge has disappeared. Iron Age metallurgy at Oppidum Saint-Vincent belongs to the same category of lost expertise. The settlement was not isolated. Imported goods discovered at the site indicate connections with broader trade networks extending toward the Mediterranean. These connections likely brought not only products but also ideas, technologies, and technical knowledge. This raises additional questions. Did metallurgical techniques arrive through trade contacts? Were specialist craftsmen traveling between settlements? Did technological innovations spread across Celtic Europe through commercial networks? Researchers know trade played a major role in transmitting knowledge throughout the ancient world. However, the exact mechanisms remain difficult to reconstruct. The archaeological record preserves artifacts but rarely preserves conversations, instructions, or training methods. Gini Fortress is a medieval stronghold perched atop a volcanic mesa in central Armenia, overlooking the Hrazdan River Valley, about 35 kilometers north of Yerevan. From a distance, the fortress appears almost impossible to reach. Sheer cliffs protect most of its perimeter, transforming the mountain itself into a natural fortress. Yet the greatest mystery of Bini is not its walls, but a hidden tunnel descending through solid rock toward the river below, a feat of engineering that continues to puzzle researchers centuries after the fortress fell silent. The ruins were known to local inhabitants for generations, but systematic archaeological investigations during the 20th century revealed the true complexity of the fortress. Researchers documented fortification walls, water reservoirs, churches, residential structures, and most importantly, evidence of a concealed passage connecting the summit to the river system below. This discovery transformed Bini from a typical medieval fortress into one of the most intriguing engineering sites in the Caucasus. The first and greatest mystery is the secret tunnel itself. Throughout history, water determined the fate of fortresses. Military historians estimate that a garrison deprived of water could collapse within days, regardless of the strength of its defenses. This problem was especially severe in mountain fortresses, where high ground provided security, but often lacked reliable water sources. Bini appears to have solved this problem through an engineering solution that remains only partially understood. The tunnel descends from the fortress plateau toward the Hrazdan River below. During a siege, defenders could theoretically reach water without exposing themselves to enemy forces. Similar systems existed at famous strongholds such as Masada in Israel, Derinkuyu in Turkey, and certain Crusader castles in the Levant. However, Bini presents a unique challenge because the tunnel was constructed within a steep rocky environment where surveying errors could easily render the entire project useless. Modern engineers solving a similar problem would typically rely on topographic maps, laser measurements, GPS positioning, geological surveys, and computer modelling. Medieval builders possessed none of these tools, yet they somehow managed to create a passage that connected the fortress with a reliable water source. The fundamental question remains unanswered. How did they know where to dig? Even a small surveying error at the surface could become a major deviation after tens or hundreds of meters of excavation. Ancient tunnel builders elsewhere often relied on shafts, visual markers, rope measurements, and geometric calculations. Archaeologists suspect that the engineers of Bini employed sophisticated surveying techniques, but no written manuals survive to explain their methods. This mystery becomes even more impressive when compared with other ancient engineering achievements. The builders of the Eupalinian tunnel on the Greek island of Samos managed to excavate a 1-kilometer water tunnel from opposite directions around 2,500 years ago. The Roman Empire built extensive aqueduct networks spanning hundreds of kilometers, yet both civilizations left at least some evidence of their engineering traditions. The builders of Bini left almost nothing behind except the structure itself. Another unanswered question involves excavation technology. The volcanic and sedimentary rock formations surrounding Bini are not easily penetrated. Medieval workers would have relied primarily on iron tools, hammers, chisels, wedges, and possibly fire-setting techniques in which rock was heated and then rapidly cooled to induce cracking. Such methods were labor-intensive and slow. Experimental archaeology suggests that excavating even a small tunnel through hard rock using pre-industrial tools can require thousands of labor hours. If the Bini tunnel required excavation through substantial sections of bedrock, the project would have demanded careful planning, organized labor, and technical expertise. Questions such as who supervised such a project, how the workforce was organized, and how long construction required remain unanswered because no surviving records provide explanations. The second mystery concerns water management. Archaeological surveys have identified large water reservoirs inside the fortress complex. One reservoir still preserves portions of its vaulted stone roof. The existence of these structures suggests that the defenders did not rely solely on the secret tunnel. Instead, they appear to have maintained a multi-layered water security system. This approach resembles strategies used in some of history's most advanced defensive sites. The Nabateans at Petra developed sophisticated water collection networks in an arid environment receiving less than 150 millimeters of annual rainfall. Byzantine engineers built underground cisterns beneath Constantinople capable of storing enormous quantities of water. Bini appears to represent a smaller but highly strategic version of the same principle. Researchers still do not know the original storage capacity of the reservoirs, nor do they fully understand the waterproofing materials used inside them. If the fortress housed hundreds of defenders during emergencies, water demand would have been significant. A single person typically requires several liters of water daily merely for survival, and over weeks or months of siege, total consumption could become enormous. The third mystery involves the fortress location itself. Bini occupies one of the most defensible positions in Armenia. The plateau rises dramatically above surrounding terrain, creating natural barriers on multiple sides. However, constructing a fortress on such a location introduced enormous logistical challenges. Every building stone had to be transported uphill, every timber beam had to be hauled to the summit, and every food supply required continuous transportation. The engineering challenge resembles problems faced by builders at Machu Picchu in Peru or certain Celtic hill forts in Europe. In all cases, the question remains similar. Why choose a location so difficult to build upon? The answer was likely strategic control. From Bini, observers could monitor movement through the Hrazdan Valley and surrounding mountain routes. In an age when communication depended on visibility and line-of-sight signaling, elevation provided immense military advantages. The fourth mystery concerns earthquake resistance. Armenia lies within a tectonically active region and has experienced destructive earthquakes throughout recorded history. The 1988 Spitak earthquake, for example, reached a magnitude of 6.8 and caused catastrophic damage across northern Armenia. Yet portions of Bini's masonry structures survived centuries of seismic activity. This raises important questions regarding medieval construction methods. Did builders intentionally incorporate flexible design principles? Were certain stone-laying techniques more resistant to seismic forces? Modern structural engineers studying historical masonry often discover surprisingly effective design features developed long before formal engineering science existed. What do you think was the most impressive achievement of Bini Fortress? The secret tunnel to the river, the advanced water management system, or the lost engineering knowledge that made the entire fortress possible? Share your thoughts in the comments below. Michelsberg, overlooking the Rhine Valley in present-day Germany, should not have existed in the form archaeologists discovered it. More than 6,000 years ago, long before metal tools, writing, or wheeled transport became widespread in Europe, people associated with the Michelsberg culture were constructing enormous earthworks, organizing large labor forces, exploiting distant resources, and mastering stone technologies whose full complexity remains only partially understood today. The greatest mystery is not that they built monumental structures. The mystery is how they acquired and preserved the knowledge required to build them. The site known as Michelsberg was identified during 19th century archaeological investigations near Bruchsal in southwestern Germany. Excavations eventually revealed evidence of a major Neolithic culture that flourished between approximately 4,400 and 3,500 BC. Over time, archaeologists discovered hundreds of settlements, enclosures, and ritual sites across modern Germany, France, Belgium, and neighboring regions, revealing that Michelsberg represented one of the largest cultural networks in prehistoric Europe. What emerged was not a collection of isolated villages, but a civilization-scale system whose technological capabilities remain surprisingly difficult to explain. One of the first puzzles concerns the enormous enclosures built by Michelsberg communities. Across Central Europe, archaeologists have identified large, circular and oval earthworks surrounded by ditches and embankments. Some enclosures extend hundreds of meters across. Constructing them required removing thousands of cubic meters of soil. This achievement becomes remarkable when considering the available technology. No iron tools existed. No bronze tools existed. Most excavation work would have relied on antler picks, stone tools, wooden shovels, and human labor. Experimental archaeology suggests that digging a single cubic meter of compact soil using primitive tools can require several hours of work. Some Michelsberg enclosures contain ditches measuring thousands of cubic meters in volume. The labor investment may have reached tens of thousands of working hours. The comparison with later civilizations is striking. Roman engineers possessed metal tools, roads, and organized administrations. Yet 6,000 years ago, Michelsberg communities were already coordinating projects on a scale requiring careful planning and leadership. Exactly how these labor forces were organized remains unknown. Equally puzzling is the placement of Michelsberg sites. Many settlements occupy elevated positions overlooking valleys, rivers, and transportation corridors. The locations appear strategically chosen to maximize visibility and communication across the landscape. Modern surveyors use maps, satellite imagery, GPS systems, and mathematical calculations. Neolithic builders possessed none of these technologies. Yet many Michelsberg sites demonstrate an understanding of terrain that appears remarkably sophisticated. Archaeologists have proposed that builders used visual sightlines, wooden markers, ropes, and accumulated local knowledge. However, the precision with which some sites exploit natural topography suggests a surveying tradition far more advanced than the surviving evidence can directly demonstrate. The knowledge behind these decisions vanished thousands of years ago. Only the results remain. Many Michelsberg enclosures appear defensive at first glance. They possess ditches. They occupy elevated ground. They define large enclosed spaces. But closer examination creates problems. Numerous ditches contain multiple entrances. Some lack continuous defensive barriers. Others seem poorly suited for military protection. If defense was their primary purpose, the designs appear surprisingly inefficient. Researchers therefore propose alternative explanations. The enclosures may have served as ceremonial gathering places. They may have functioned as trade centers. They may have hosted seasonal festivals, religious rituals, or political assemblies. Some sites may have combined all of these functions simultaneously. The problem is that no written records survive. Archaeologists can measure the ditches, map the structures, and analyze artifacts, but they cannot directly access the intentions of the builders. The Michelsberg world was far larger than archaeologists once believed. Chemical and geological analyses reveal that stone materials often traveled significant distances. Some flint artifacts originated from sources located many tens or even hundreds of kilometers away. Exotic materials circulated through extensive exchange networks linking communities across Central Europe. This creates another puzzle. Transporting raw materials over such distances required organization, communication, and social cooperation. The challenge becomes even greater considering the absence of roads, carts, and draft animals on the scale known from later periods. How information traveled across these networks remains poorly understood. How trade agreements were maintained remains unknown. How resources were distributed remains largely invisible. Yet the archaeological evidence demonstrates that the system worked. Perhaps the most fascinating technological mystery of Michelsberg concerns flint. To modern observers, flint tools often appear simple. In reality, they represent one of the most sophisticated material technologies ever developed without metal. Michelsberg craftsmen produced blades, scrapers, knives, and specialized tools displaying remarkable precision. Many artifacts reveal carefully controlled fractures and highly standardized shapes. Creating such tools required deep knowledge of material behavior. Flint does not break randomly. It fractures according to complex mechanical principles involving force direction, angle of impact, internal structure, and energy transfer. Modern materials scientists describe this process as conchoidal fracture. A mistake of only a few degrees can ruin an entire tool. Yet Michelsberg knappers repeatedly achieved results that demonstrate extraordinary consistency. The mystery begins with raw material acquisition. How did miners identify the highest quality flint deposits? Some sources were buried beneath layers of sediment and soil. Locating them required geological knowledge accumulated through generations of observation and experience. Evidence from Neolithic Europe demonstrates that flint mining could become a major industrial activity. At sites such as Spiennes in Belgium and Grimes Graves in Britain, prehistoric miners excavated shafts reaching depths of more than 10 meters. Although not every mine belonged directly to Michelsberg communities, these sites demonstrate the technological environment in which they operated. The challenge was not simply finding flint. The challenge was extracting it safely. Underground mining requires ventilation, structural stability, lighting, and navigation. Even today, underground work remains hazardous. How Neolithic miners managed these risks remains only partially understood. After extraction came transportation. Large flint nodules sometimes weighed tens of kilograms. Moving them across long distances required logistics systems that left few traces in the archaeological record. Then came manufacturing. Experimental archaeologists attempting to replicate prehistoric blades often require years of practice before achieving consistent results. Master craftsmen can produce long, thin blades with astonishing efficiency. Many Michelsberg artifacts suggest the existence of similarly skilled specialists. This raises another question. How was knowledge transmitted? There were no manuals, no technical diagrams, no written instructions. Every technique had to be learned through demonstration, observation, and practice. Entire technological systems existed only inside human memory. One generation taught the next. When those chains of transmission eventually broke, much of the knowledge disappeared forever. Today, archaeologists can recreate some techniques through experimentation, but many details remain uncertain. Exactly how apprentices were trained, exactly how quality standards were maintained, exactly how production was organized. These questions remain unanswered. Another unresolved puzzle involves human remains discovered in ditches and enclosure features. In several locations, archaeologists uncovered skeletal material deposited in unusual ways. Some remains appear incomplete. Others were placed in contexts that differ from conventional burials. These discoveries have generated intense debate. Were they ritual offerings, secondary burials, ancestor ceremonies, evidence of social conflict? No single explanation accounts for every case. The archaeological record preserves the physical remains but not the beliefs that produced them. What do you think was the most impressive achievement of the Michelsberg culture? The giant earthworks, the vast trade networks, or the lost flint technology that allowed Neolithic craftsmen to master stone with extraordinary precision? Karakin Grad in southern Serbia was a fully planned Byzantine city that appeared in the 6th century AD, equipped with walls, churches, streets, reservoirs, and an advanced water network. Less than a century later, it was abandoned. The city survived, but the knowledge behind it did not. The ruins were identified in the early 20th century and are now widely accepted as Justiniana Prima, the city founded by Byzantine Emperor Justinian I around AD 535. Decades of excavations have revealed one of the most ambitious urban projects of late antiquity. Karakin Grad stands about 30 kilometers southwest of modern Leskovac in Serbia. Unlike Constantinople, Thessaloniki, or other major Byzantine centers, it was not built beside a major seaport, a large river, or an established trade route. Yet archaeological evidence shows that it was designed as a major administrative, religious, and political center from the very beginning. The city covered roughly 40 hectares and was protected by multiple defensive walls. Inside were churches, administrative buildings, workshops, residential districts, paved streets, drainage systems, and public infrastructure. The urban layout was carefully organized rather than gradually developed. This immediately creates a mystery. Most ancient cities evolved over centuries, but Karakin Grad appears to have been planned almost entirely before construction began. The project resembles a modern planned capital, more than a typical ancient settlement. The comparison is striking. When Emperor Constantine established Constantinople in the 4th century, he expanded an existing city. Karakin Grad, by contrast, was essentially created from scratch. Why invest enormous resources into constructing a major city in a relatively remote region of the Balkans? Historical sources suggest Justinian wanted to honor the region of his birth. Yet many historians believe the scale of construction exceeded what would have been necessary for symbolism alone. The city appears to have been designed as a regional centre, capable of projecting imperial authority into a strategically important frontier zone. Even then, the size of the investment remains difficult to explain. Among all the enigmas surrounding Karasingrad, none is more fascinating than its hydraulic engineering. Water is the most fundamental requirement for any city. Without a reliable supply, urban life collapses, and this problem becomes even more difficult on elevated terrain, where natural water sources are limited. Excavations revealed an extensive hydraulic network consisting of aqueducts, channels, cisterns, reservoirs, drainage systems, and distribution infrastructure integrated throughout the city. The challenge was enormous. Engineers had to transport water across uneven terrain while maintaining a precise gradient. If the slope was too steep, water would erode channels and damage structures. If the slope was too shallow, flow could stop entirely. Modern hydraulic engineers understand how difficult this balancing act can be, as even a deviation of a few centimeters over long distances can significantly affect performance. Yet 6th century Byzantine engineers managed to create a functioning system without laser levels, GPS receivers, computer models, or modern surveying equipment. How they achieved this remains one of the site's greatest mysteries. No detailed engineering manuals survive to explain their methods. Researchers believe surveyors relied on instruments derived from Roman technology, including water levels, plumb lines, measuring rods, and sighting devices. However, exactly how they achieved the necessary precision remains uncertain. The Roman Empire built famous aqueducts such as the Pont du Gard in France and the Aqua Claudia in Italy. These systems demonstrated extraordinary surveying accuracy, and Karasingrad suggests that similar expertise survived into the Byzantine period. The mystery is that the city was constructed during an era often described as a time of political instability and military pressure. Despite these challenges, engineers successfully implemented a sophisticated water infrastructure comparable to systems found in much larger urban centres. The reservoirs themselves raise further questions. Archaeologists have discovered large storage facilities designed to regulate supply during seasonal fluctuations. Their placement indicates a deep understanding of water management, pressure control, and urban distribution. Some researchers argue that the hydraulic system was over-engineered relative to the city's relatively short existence. If true, the builders may have anticipated substantial future growth that never occurred. The city ultimately vanished, but the water system remained as evidence of technical knowledge that is only partially understood today. Building a city is difficult, but building an entire city within a few decades is extraordinary. Construction at Karasingrad included defensive walls, towers, churches, roads, public squares, housing districts, drainage networks, and hydraulic infrastructure. Such a project required vast quantities of stone, timber, brick, lime mortar, and skilled labour. Archaeological studies indicate that much of the city was completed in a remarkably short period after its foundation around AD 535. The logistics are staggering. Thousands of workers may have been involved. Stone had to be quarried, transported, shaped, and assembled. Lime production required large amounts of fuel, and bricks had to be manufactured in significant quantities. The challenge can be compared to other imperial construction projects. The Hagia Sophia in Constantinople was completed in approximately 5 years under Justinian. Karasingrad demonstrates that the empire was simultaneously capable of supporting large-scale construction hundreds of kilometers away. Exactly how construction was organized remains unclear. No surviving records explain labor management, material supply chains, or project coordination. The city appears almost as a physical demonstration of engineering capability, whose documentation has disappeared. The city's layout reveals careful planning at multiple scales. Major streets connected administrative districts, religious buildings occupied strategically important positions, defensive structures exploited natural topography, and infrastructure was integrated into the overall design. Such coordination required accurate surveying. Modern archaeologists using aerial photography, GIS mapping, and digital reconstruction have shown that the city's organization was far from random. This raises another question. How sophisticated were Byzantine surveying methods in the 6th century? The builders clearly understood geometry, elevation, alignment, and land assessment. Yet the practical techniques used to transform these concepts into a functioning city remain poorly documented. The situation resembles other ancient engineering mysteries. The Great Pyramid demonstrates extraordinary geometric precision. Roman roads maintained remarkably consistent gradients over long distances, and the builders of Machu Picchu adapted architecture to complex mountain terrain. Karatin Grad belongs to the same tradition of ancient engineering achievements whose technical details are only partially preserved. Perhaps the most puzzling question is why such an ambitious city survived for such a short time. Evidence suggests Karatin Grad flourished during the 6th century. Then, during the early 7th century, it was abandoned. Several explanations have been proposed. Avar invasions may have destabilized the region, Slavic migrations altered demographic patterns, economic disruption weakened imperial control, and military priorities shifted elsewhere. Yet none of these explanations fully resolves the mystery. Cities facing similar pressures sometimes survive for centuries. Karatin did not. The contrast between the enormous investment in infrastructure and the city's brief lifespan remains one of the most striking aspects of the site. It is as if a grand experiment in urban planning was suddenly interrupted. What do you think was the greatest achievement of Karatin? The advanced water system, the remarkable urban planning, or the lost engineering knowledge that made the entire city possible? Share your thoughts in the comments below. Baltinglass Passage Tomb is a 5000-year-old megalithic monument standing on Baltinglass Hill in County Wicklow, Ireland. More than 380 metres above sea level, it occupies one of the most commanding viewpoints in Eastern Ireland. For over 5 millennia, the monument has overlooked valleys, rivers, mountains, and ancient travel routes. Yet the greatest mystery is not the tomb itself. It is how Neolithic builders, working without metal tools, wheeled vehicles, maps, or written language, selected this exact location and created a monument whose engineering logic remains only partially understood today. The site was recorded by antiquarians centuries ago and later investigated through archaeological surveys and excavations. Researchers identified a large passage tomb surrounded by substantial cairn of stone. Radiocarbon evidence places its construction around 3000 BC, making it broadly contemporary with Ireland's great megalithic centres such as Newgrange and Noath. However, unlike those famous monuments located in the Boyne Valley, Baltinglass occupies a high mountain landscape, raising questions that archaeologists still struggle to answer. The first mystery begins with location. Ancient builders did not place the monument in fertile farmland beside a river or near a major settlement. Instead, they chose the summit of a steep hill, rising hundreds of meters above the surrounding countryside. From a modern perspective, this decision appears irrational because transporting construction material uphill requires dramatically more labor than building on level ground. Every stone carried upward increases the logistical challenge. Yet the builders intentionally selected one of the most difficult locations available. Why? The answer may lie in what the summit reveals. Modern geographic analysis shows that Baltinglass Hill provides visibility across a vast region of Eastern Ireland. On clear days, observers can see large portions of County Wicklow and neighbouring landscapes. The tomb occupies a position that dominates the surrounding terrain. This leads directly to the second and perhaps greatest mystery of Baltinglass, the lost science of landscape surveying. Today, engineers use satellites, drones, GPS receivers, topographic maps, digital elevation models, and computer software to identify optimal locations. Neolithic builders possessed none of these technologies. Yet the placement of Baltinglass suggests a sophisticated understanding of terrain that rivals the strategic planning seen in much later societies. Researchers studying prehistoric monuments increasingly believe that ancient builders were not simply constructing tombs, they were designing landscapes. Baltinglass appears to be part of a wider visual network connecting mountains, valleys, ceremonial sites, and natural landmarks. The monument's position may have been selected after generations of observation and accumulated environmental knowledge. The technical challenge is staggering. To identify the best viewpoint across hundreds of square kilometers, surveyors would have needed to explore the landscape extensively. They would have needed to compare sightlines from multiple hilltops, evaluate visibility under changing weather conditions, and understand how sunlight interacted with the terrain throughout the year. This process resembles large-scale geographic surveying, yet no measuring instruments have survived, no manuals exist, and no written records explain the methods. Archaeologists know the result, but not the process. The comparison with other ancient sites is remarkable. The builders of Stonehenge selected a location connected to surrounding horizons. The creators of Machu Picchu integrated architecture into mountain topography. The engineers of the Nazca Lines designed geometric figures visible across vast landscapes. Baltinglass belongs to the same tradition of monumental landscape engineering, but it predates many famous examples by thousands of years. Even more intriguing is the possibility that the monument served as a navigational landmark. Before roads, maps, and written directions, elevated monuments could function as reference points visible from great distances. Baltinglass may have helped organize movement through the landscape, acting as a fixed marker in a world where permanent landmarks were essential for orientation. If true, the monument represents not only architecture but also an ancient information system. The third mystery involves transportation technology. The original cairn is estimated to have measured approximately 30 to 35 meters in diameter. Constructing such a monument required moving enormous quantities of stone to the summit. The challenge becomes clear when compared to experimental archaeology. Modern reconstruction projects have shown that moving even a single multi-ton stone with ropes and wooden sledges requires coordinated teams and careful planning. Transporting hundreds or thousands of stones uphill multiplies the difficulty enormously. Yet the builders succeeded. Exactly how they organized labor remains unknown. Some researchers propose wooden rollers, others suggest sledges pulled across prepared tracks, and still others believe seasonal conditions may have played a role, with frozen ground reducing friction during transport. No consensus exists, and the engineering solution vanished long ago. The fourth mystery concerns astronomical knowledge. Like many megalithic monuments throughout Ireland, Baltinglass appears to have been positioned with careful attention to the surrounding horizon. Neolithic societies repeatedly demonstrated an ability to track solar cycles. Newgrange famously illuminates its inner chamber during the winter solstice, and similar alignments appear at monuments throughout Britain and Ireland. Baltinglass occupies a summit where horizon observations would have been exceptionally effective. This raises a difficult question. How did people without clocks, telescopes, mathematics, textbooks, or written calendars develop such precise knowledge of celestial cycles? Astronomers note that identifying recurring solar positions requires observations extending across many years. Knowledge had to be preserved and transmitted across generations. The monument, therefore, suggests a long tradition of systematic observation. The fifth mystery is social organization. Large construction projects require more than technical knowledge. They require leadership, logistics, food production, and labor coordination. Baltinglass was built during a period when populations were relatively small, yet the monument represents thousands of hours of collective work. Who organized this effort? Was there a ruling elite, religious specialists, engineering experts? Or was construction coordinated through community cooperation? Archaeology provides clues, but no definitive answers. The social mechanisms behind the project remain hidden. Horem's citadel, located in the Shirak plain of northwestern Armenia, rises from a volcanic landscape where some of the largest fortifications of the ancient Caucasus still guard secrets that archaeologists cannot fully explain. Known to local inhabitants for centuries, Horem attracted systematic archaeological investigation during the 20th century. Excavations revealed a vast fortified complex occupied from the late Bronze Age through the Urartian period, exposing massive defensive walls, residential areas, storage facilities, workshops, and evidence of advanced metal production. At first glance, Horem appears to be another hilltop stronghold, but closer examination reveals something far more remarkable. The site covers an extensive fortified area protected by multiple defensive circuits. Archaeologists have identified occupation phases stretching from roughly the 2nd millennium BC into the 1st millennium BC. During this period, much of the surrounding region consisted of competing tribal societies and emerging kingdoms. Yet Horem demonstrates a level of organization that seems unusually sophisticated for its age. Constructing such a complex required thousands of tons of stone. Labor had to be coordinated, building materials had to be transported, and defensive systems had to be planned across an entire landscape rather than around a single structure. The comparison with contemporary sites is striking. Many Bronze Age settlements in the Caucasus consisted of relatively small fortified villages. Horem, by contrast, resembles a regional centre capable of controlling surrounding territory. The first mystery therefore emerges immediately. Who organised construction on such a scale, and what administrative system made it possible? No surviving inscriptions explain the process. No architectural manuals remain, and the planners disappeared, leaving only the stone behind. One of the most puzzling aspects of Horem is its placement. The fortress occupies elevated terrain overlooking major movement corridors through the Shirak region. Modern topographic analysis demonstrates that many defensive positions maximize visibility across surrounding approaches. Today, engineers use satellite imagery, GPS systems, and digital elevation models to identify optimal observation points. Ancient builders possessed none of these technologies, yet Horem's defensive layout suggests a detailed understanding of terrain. Researchers studying ancient fortifications frequently encounter this problem. Similar questions surround sites such as the hill forts of Iron Age Europe and the massive defensive networks of Urartu. Somehow, ancient surveyors repeatedly identified locations that modern computer models often confirm as strategically ideal. How was this accomplished? Some scholars propose generations of accumulated local knowledge, while others suggest systematic surveying techniques involving sightlines, marker poles, and geometric measurement methods now lost to history. The exact answer remains unknown. Armenia lies within one of the most seismically active regions of Western Asia. Throughout history, earthquakes have repeatedly damaged cities across the Armenian highlands, and modern seismic studies confirm the presence of active fault systems throughout the region. This makes Horem's survival particularly intriguing. Although many structures collapsed long ago, significant portions of defensive architecture remained recognizable for thousands of years. The builders appear to have understood several principles that improve structural stability, including large stone foundations, careful adaptation to bedrock, terrace construction following natural contours, and the distribution of structural loads across thick walls. These features do not prove the existence of formal earthquake engineering. However, they suggest generations of practical experimentation with construction in a hazardous environment. The same pattern appears elsewhere in history. In Peru, the builders of Machu Picchu developed masonry that resisted earthquakes remarkably well. In Japan, traditional wooden architecture evolved methods for surviving seismic activity. At Horom, similar adaptation may have emerged independently. The question is whether ancient builders consciously understood the underlying principles or simply arrived at effective solutions through centuries of experience. Perhaps the most underestimated mystery involves logistics. Moving stone is difficult, and moving thousands of tons of stone without modern machinery is a monumental challenge. Even a single block weighing 1 ton requires coordinated labor. Multiply that process across entire defensive systems, and the scale becomes extraordinary. Researchers studying ancient construction estimate that large fortification projects often required years or decades of organized effort. Food had to be supplied, workers had to be housed, tools had to be manufactured, and construction materials had to be distributed efficiently. This transforms Horom from a simple archaeological site into evidence of a complex economic system. Yet very little is known about the mechanisms that supported such large-scale operations. The fortress survives, but the organizational structure that created it does not. The greatest technological mystery of Horom may not be found in its walls at all. It may be hidden within traces of metal production. Excavations throughout the Armenian highlands have demonstrated that the region played a significant role in ancient metallurgy. Rich deposits of copper, iron, gold, silver and other minerals help make the area one of the most important metalworking zones of the ancient Near East. Evidence associated with Horom suggests participation in this broader metallurgical tradition. This raises an extraordinary question. How advanced was the technical knowledge possessed by the metalworkers who lived here? Producing high-quality bronze requires precise control of alloy composition. Copper alone is relatively soft, while adding approximately 10 to 12% tin can dramatically increase hardness and durability. Achieving this consistently is not simple. Ancient craftsmen had no thermometers, no spectrometers, and no chemical laboratories. Yet archaeological analysis across the region repeatedly reveals alloys falling within effective working ranges. The challenge becomes even greater with iron. Iron smelting requires temperatures exceeding 1,150 degrees Celsius. Furnaces must maintain controlled airflow, fuel quality must remain consistent, and ore selection affects the final product. Modern metallurgists understand these variables scientifically, while ancient craftsmen learned them through observation and experience. What remains unclear is how this knowledge was transmitted. Experimental archaeology has shown that mastering ancient smelting techniques can require years of training. Small changes in furnace design, charcoal quality, or airflow can determine success or failure. At Horom, metal workers appear to have solved these problems centuries before modern science explained them. The comparison with other ancient civilizations is revealing. Egypt produced sophisticated copper tools, Mesopotamia developed extensive bronze industries, and the Hittites became famous for ironworking traditions. Yet the Armenian highlands occupied a unique position connecting these technological worlds. Raw materials, trade routes, and specialized knowledge all converged here. Some researchers even argue that the region played a major role in spreading metallurgical innovations throughout Western Asia. If true, Huram may have participated in technological networks far larger than previously imagined. The mystery deepens further when considering the disappearance of this expertise. The furnaces vanished, the workshops collapsed, and the craftsmen died. The technical knowledge that once existed survives only indirectly through artifacts and slag deposits. Modern scientists can analyze microscopic structures within ancient metals, identify alloy compositions to fractions of a percent, and reconstruct furnace temperatures using laboratory methods. Even so, they still cannot fully reconstruct the decision-making processes that ancient metalworkers used every day. How did they judge temperature? How did they standardize production? How did apprentices learn these skills? The answers remain hidden. Metallurgy rarely develops in isolation. Metal production depends upon trade. Tin, copper, fuel, tools, food supplies, and finished goods must all move through interconnected networks. The Armenian highlands occupied a strategic position between Anatolia, Mesopotamia, Iran, and the Caucasus. Artifacts discovered throughout the region demonstrate long-distance exchange stretching hundreds of kilometers. This suggests that Huram may have been connected to economic systems extending far beyond the visible horizon. The challenge is reconstructing those connections. Ancient trade routes rarely leave permanent traces. Merchants disappear, animals die, and roads erode. Only scattered artifacts remain. Like fragments of a broken puzzle, they hint at a network whose full extent may never be known. What do you think was Huram Citadel's greatest achievement? Its massive fortifications, its advanced metalworking technology, or the lost knowledge that allowed ancient engineers to build and manage such a complex stronghold thousands of years ago? Share your thoughts in the comments below. Felix Romuliana, hidden in eastern Serbia near the modern village of Gamzigrad, should not exist where it does. Built between approximately AD 298 and AD 311 by the Roman Emperor Galerius, the complex stands far from the great capitals of the Roman Empire. Yet archaeologists have uncovered massive fortification walls, luxurious palaces, monumental temples, intricate mosaics, and engineering works worthy of Rome itself. Today, the site is recognized as a UNESCO World Heritage Site, but despite more than a century of archaeological research, some of its most important technological secrets remain unresolved. The greatest mystery is not that Felix Romuliana was built. The mystery is how such a sophisticated imperial complex appeared in a remote corner of the Balkans, using construction techniques that continue to puzzle researchers more than 1,700 years later. The ruins have been known locally for centuries, but their true identity remained unknown. Systematic archaeological excavations began in 1953 under Serbian archaeologist Dragoslav Srejovic. The breakthrough came decades later, when fragments of inscriptions revealed the name Felix Romuliana, confirming that the complex was the imperial palace built by Galerius and named after his mother, Romula. What researchers uncovered was far larger and more sophisticated than anyone expected. Behind the massive walls stood an entire ceremonial city designed for an emperor. The first mystery concerns location. Most Roman imperial residences were connected directly to major administrative centers, military frontiers, trade networks, or strategic ports. Rome, Milan, Trier, Constantinople, and Nicomedia all occupied positions of enormous political importance. Felix Romuliana did not. The site lies in the Timok Valley of eastern Serbia, hundreds of kilometers from the empire's largest urban centers. Yet, Galerius invested extraordinary resources into the project. Archaeological evidence reveals imported marble from the Mediterranean, luxury decorative stone, high-quality mosaics, bronze sculptures, and advanced hydraulic systems. Transporting such materials would have required extensive logistical planning. For comparison, constructing Diocletian's palace in modern Croatia required access to major Adriatic shipping routes. Felix Romuliana lacked such advantages. Everything had to be transported through inland routes across mountainous terrain. Researchers estimate that tens of thousands of tons of construction materials were moved to the site. The exact transportation system remains unknown. How were supply chains organized? How many workers participated? How long did construction actually take? No surviving Roman document provides definitive answers. From above, Felix Romuliana resembles a military fortress. Its defensive walls enclose roughly 6.5 hectares. The walls reach several meters in thickness and are reinforced by more than 20 towers. Massive gates controlled access from multiple directions. At first glance, the complex appears designed for warfare, yet the interior tells a different story. Instead of barracks and weapons depots, archaeologists discovered ceremonial halls, luxurious residences, temples, courtyards, mosaics, and monuments dedicated to imperial worship. This contradiction has generated decades of debate. If the complex was primarily ceremonial, why invest so heavily in military-style defences? Some historians argue that the political instability of the Tetrarchic period made security essential. Others suggest the walls had symbolic functions, projecting imperial authority rather than serving purely defensive purposes. The exact balance between military necessity and political symbolism remains uncertain. Long before the first stone was laid, Roman engineers had to design the entire complex. The layout demonstrates remarkable planning. Gates align with major internal roads. Towers are distributed with impressive regularity. Buildings occupy carefully organized positions within the enclosure. Modern surveys reveal that the overall plan maintains geometric consistency across hundreds of meters. Today, engineers can achieve such accuracy using GPS receivers, laser scanners, total stations, and digital mapping software. Roman surveyors possessed none of these tools. Instead, they relied on instruments such as the groma, chorobates, measuring rods, plumb lines, and astronomical observations. What remains unclear is how survey teams coordinated measurements across a project of this scale while maintaining such precision. No detailed technical manual survives describing exactly how the engineers responsible for Felix Romuliana executed the work. The results remain visible, but the methods remain largely invisible. Among all the mysteries of Felix Romuliana, perhaps none is more technically fascinating than its construction materials. More than 17 centuries after construction, large portions of the brickwork remain remarkably intact. Archaeological analysis has shown that Roman builders employed carefully selected clay sources and highly controlled firing processes. Many bricks display consistent density, strength, and durability, despite being produced without modern industrial equipment. This raises a difficult engineering question. How did Roman craftsmen achieve such uniform quality? Modern brick manufacturing depends on precise temperature monitoring, automated kiln controls, laboratory testing, and industrial standardization. Production temperatures typically range between 900 and 1,100 degrees Celsius. Roman builders possessed none of these technologies, yet evidence suggests they routinely achieved firing temperatures approaching or exceeding similar ranges. Microscopic analysis reveals that mineral transformations inside the bricks occurred under carefully controlled thermal conditions. Certain clay particles underwent structural changes that only happen when specific temperature thresholds are reached and maintained for extended periods. The challenge was not simply reaching high temperatures. The challenge was maintaining them consistently. A kiln operating at 1000 degrees Celsius is useless if temperatures fluctuate wildly. Uneven heating creates weak bricks, cracks, internal stresses, and inconsistent performance. Many bricks at Felix Romulliana exhibit surprisingly uniform characteristics. Researchers believe Roman craftsmen controlled airflow, fuel distribution, kiln geometry, stacking arrangements, and firing duration with exceptional skill. However, the precise operational procedures remain uncertain. No Roman engineer left a detailed instruction manual. Experimental archaeologists have attempted to recreate ancient kilns using historical methods. The results demonstrate that skilled operators can achieve impressive consistency, but reproducing Roman quality often proves difficult and unpredictable. The mystery becomes even greater when considering scale. Felix Romulliana required millions of bricks. Producing such quantities demanded reliable systems capable of maintaining standards across thousands of firing cycles. The site also contains sophisticated mortar technology. Chemical studies indicate carefully balanced mixtures of lime, aggregates, and local materials. Some mortars exhibit extraordinary longevity, surviving freeze-thaw cycles, groundwater exposure, and centuries of environmental stress. The comparison with modern materials is striking. Many 20th century concrete structures show significant deterioration after less than 100 years, while portions of Roman construction remain standing after 17 centuries. Scientists can analyze the chemistry. They can measure mineral composition. They can model kiln temperatures. Yet the practical knowledge that allowed ancient craftsmen to repeatedly achieve these results may never be fully recovered. Felix Romulliana contains some of the finest mosaics discovered in the Balkans. Scenes depicting Dionysus, labyrinth motifs, hunting imagery, and mythological subjects display extraordinary craftsmanship. Thousands of stone and glass tesserae were cut, sorted, transported, and assembled with astonishing precision. Some decorative programs rival those found in major imperial centers such as Rome and Antioch. This creates another puzzle. Did specialized craftsmen travel from distant regions of the empire? Or did local workshops possess technical abilities far beyond what historians previously assumed? The archaeological evidence remains inconclusive. Either answer would significantly alter our understanding of artistic and technological networks within the late Roman Empire. The final mystery lies beyond the palace walls. On nearby Magura Hill, archaeologists discovered ceremonial structures associated with the deification of Galerius and his mother Romula. The placement appears deliberate. The palace below functioned as the earthly center of power, while the hill above served as the symbolic gateway to divine status. This relationship required large-scale planning across the landscape. Researchers continue debating whether the entire complex was conceived as a unified ceremonial machine designed to transform imperial authority into sacred legitimacy. If true, Felix Romulliana was not merely architecture, it was political engineering expressed through stone. Altkönig Ringwall stands on the summit of Altkönig Mountain in Germany's Taunus Range. More than 2,000 years ago, Iron Age builders carried thousands of tons of stone to nearly 800 meters above sea level and created one of the largest fortified hilltop complexes in Central Europe. The walls still survive, but the knowledge that built them does not. The earthworks were known locally for centuries, But systematic archaeological investigations began during the 19th century as scholars recognized the site as a major Celtic hill fort, dating to the late Iron Age, roughly between the 4th and 1st centuries BC. At first glance, Altkönig appears to be a straightforward defensive fortress. The site occupies one of the highest peaks in the Taunus Mountains, approximately 798 meters above sea level. From the summit, visibility extends across large portions of western Germany, allowing any approaching enemy to potentially be detected long before arrival. However, the location creates a problem. Everything required for construction had to be transported uphill. Stone, timber, food, tools, water containers, and construction materials all had to reach a mountaintop with no modern roads and no mechanical transport systems. Archaeologists estimate that the defensive system enclosed more than 100 hectares of terrain through multiple concentric walls and earthworks, and even conservative calculations suggest the movement of tens of thousands of tons of stone. The question remains unanswered. Why would Iron Age communities choose one of the most difficult locations imaginable for a construction project of this scale? The comparison with other European hill forts is revealing. Sites such as Maiden Castle in England and Bibracte in France also occupy elevated positions, but Altkonig's combination of altitude, rugged terrain, and extensive fortifications represents an extraordinary engineering commitment. The builders clearly believed the strategic advantages outweighed the immense logistical challenges, yet how they reached that conclusion remains uncertain. The most fascinating mystery at Altkönig involves the construction technique known as Murus Gallicus. The Roman commander Julius Caesar described this engineering method during his campaigns against Celtic tribes in Gaul during the 1st century BC. According to his observations, Celtic fortifications often consisted of a sophisticated combination of timber beams, stone facings, and iron fasteners. For centuries, historians underestimated this technology, but modern archaeology has produced a very different picture. Unlike simple stone walls, Murus Gallicus functioned as a composite structure in which massive horizontal timber beams formed an internal framework. Large stones filled and covered the exterior, and iron spikes and connectors locked the system together. From an engineering perspective, this design was remarkably advanced. Stone provides compressive strength, timber absorbs shock and distributes force, and iron connections prevent structural separation. Together, these materials create a defensive barrier capable of resisting impacts that would crack or destabilize conventional masonry. Experimental archaeology has demonstrated that composite timberstone structures can absorb significantly more energy than dry stone walls, and some engineers compare the concept to modern reinforced construction, where different materials compensate for one another's weaknesses. Yet the most important question remains unanswered. How did Iron Age builders develop this knowledge? The Celts left no engineering manuals, no design drawings survive, and no mathematical calculations have been discovered. Even today, researchers debate fundamental questions regarding how dimensions were standardized, how load-bearing sections were determined, how much variation existed between different construction crews, and how iron connectors were manufactured in sufficient quantities. The mystery becomes even deeper when considering scale. A large Murus Gallicus wall required enormous quantities of timber. Thousands of trees may have been harvested, processed, transported, and assembled into precise structural frameworks. This implies planning systems far beyond what many people associate with prehistoric Europe. The wall itself survives, but the engineering knowledge behind it does not. Building walls is one challenge, but placing them correctly is another. The defensive circuits at Altkönig follow the natural contours of the mountain with remarkable effectiveness. The walls maximize defensive advantages while minimizing vulnerable approaches. Modern engineers achieve such optimization using topographic maps, satellite imagery, GPS measurements, and computer models. Iron Age builders possessed none of these tools, yet they somehow identified the most advantageous routes for defensive barriers across hundreds of hectares of rugged terrain. Researchers have proposed the use of sighting poles, rope measurements, observation points, and geometric surveying techniques. However, no consensus exists. The problem resembles mysteries found at other ancient sites. The builders of the Great Pyramid achieved astonishing alignment accuracy. Roman military engineers created roads stretching across continents, and the Cretans of Altkönig may have possessed their own specialized surveying traditions that disappeared long ago. Every stone in Altkönig represents transportation, every timber beam represents labor, and every iron fastener represents industrial production. Together, they reveal a hidden logistical system. Archaeologists estimate that large Iron Age hill forts required coordinated labor involving hundreds or potentially thousands of individuals. Food had to be supplied, raw materials had to be acquired, and construction schedules had to be organized. This raises an important question. Who coordinated these operations? The popular image of loosely organized Celtic tribes does not easily explain projects on this scale. The evidence suggests sophisticated social organization. Some researchers argue that sites such as Altkönig functioned as regional political centers capable of mobilizing large populations, while others propose that construction occurred gradually across generations. Neither explanation fully solves the problem. The engineering remains visible, but the management system behind it remains largely invisible. Perhaps the most practical mystery concerns water. A fortified hilltop settlement cannot survive without reliable access to water supplies, and at nearly 800 meters elevation, this challenge becomes particularly severe. Modern military planners consider water one of the most critical requirements for any defensive installation, and ancient builders faced the same reality. Researchers continue investigating whether Altkönig relied on springs, reservoirs, rainwater collection systems, or seasonal occupation patterns. The available evidence remains incomplete. If large populations occupied the site regularly, some form of sophisticated water management almost certainly existed. Exactly what form that system took remains uncertain. Evidence from Celtic Europe demonstrates extensive iron production during the late Iron Age, and Altkönig was almost certainly connected to this technological network. Iron tools were required for woodworking, iron fasteners were needed for Murus Gallicus construction, and iron weapons equipped defenders. Producing iron is far from simple. Bloomery furnaces must reach temperatures exceeding 1,100 degrees Celsius. Ore quality must be controlled, and charcoal production requires careful resource management. The technological expertise involved was considerable, yet the craftsmen responsible left almost no written records. This creates a recurring pattern in archaeology. The products survive, but the knowledge systems disappear. Even after decades of research, scholars continue debating Altkönig's primary function. Was it a permanent settlement, a military stronghold, a political center, a ceremonial location, or a regional refuge during times of conflict? Each theory explains some evidence while leaving other questions unresolved. If the site housed large permanent populations, where is the corresponding domestic evidence? If it served only as a refuge, why invest so heavily in construction? If it functioned as a political center, how extensive was its influence? No single explanation fully accounts for all available data. Amantia is located in southern Albania, approximately 34 kilometers southeast of the Bay of Vlor, on a rocky hill rising about 600 meters above sea level. The ruins were known locally for centuries, but systematic archaeological investigations began during the 20th century, revealing one of the most remarkable urban centres of ancient Illyria. What archaeologists uncovered was unexpected. Massive defensive walls, a sophisticated urban layout, public buildings, a stadium, temples, and evidence of advanced engineering emerged from a mountain landscape where few would expect a major ancient city to thrive. More than 2,000 years later, many questions about how Amantia was built remain unanswered. The first mystery begins with the city's location itself. Most major ancient cities develop near rivers, fertile plains, coastlines, or trade routes where transportation and agriculture were easier. Amantia did the opposite. Its builders selected a steep mountainous plateau surrounded by difficult terrain. From an engineering perspective, this decision created enormous challenges. Every stone, every timber beam, every tool, every food supply, and every construction material had to be transported uphill. Modern engineers understand the logistical difficulties involved in building large infrastructure projects in mountainous regions. Even with trucks, cranes, and paved roads, transporting construction materials through steep terrain remains expensive. Yet during the 4th and 3rd centuries BC, the inhabitants of Amantia transformed an exposed hilltop into a thriving urban centre. Researchers estimate that thousands of tons of stone were used throughout the city. The question is simple but profound. Why choose such a difficult location, and how did they manage the enormous logistical burden? Military security explains part of the answer. The elevation provided commanding views across the surrounding valleys and routes leading toward the Adriatic coast. However, strategic advantage alone does not explain how the construction was achieved. The technical knowledge required to establish a city under such conditions remains one of Amantia's greatest mysteries. The most visible evidence of that knowledge survives in the city's fortifications. Amantia was enclosed by walls extending approximately 2.1 kilometers. In some sections, the walls reached heights of several meters and were built using carefully shaped limestone blocks. These fortifications were not random accumulations of stone. They followed the contours of the terrain while maximizing defensive effectiveness. Archaeologists studying the walls have noted the remarkable precision of the masonry. The builders created structures capable of surviving earthquakes, weathering erosion, warfare, and more than 2 millennia of exposure. Comparisons with other ancient fortifications reveal the scale of the achievement. Many settlements of comparable population possessed far smaller defensive systems. Yet Amantia invested enormous resources in its walls. The mystery becomes even greater when considering the workforce required. Without cranes, steel tools, or mechanized transport, moving and positioning large stone blocks demanded careful planning and organization. Experimental archaeology has shown that transporting multi-ton stones with ancient technology is possible, but it requires large labor forces, sophisticated coordination, and significant engineering expertise. No written records explain how the builders of Amantia organized these operations. The walls survive, but the instructions do not. Before any wall could be built, someone had to map the landscape. This may be one of the least visible but most impressive achievements of Amantia. The city occupies uneven terrain filled with slopes, ridges, and natural obstacles, yet the urban layout demonstrates careful planning. The walls follow strategic lines. Public spaces occupy practical locations, and access routes connect different sectors efficiently. Such organization required surveying. Today, surveyors use GPS satellites, laser scanners, drones, and digital terrain models. Ancient engineers possessed none of these technologies, Instead, they relied on simple instruments, geometry, observation, and experience. The question is how accurate those methods could be. Studies of ancient Greek and Roman engineering have demonstrated that surprisingly precise measurements could be achieved using basic tools such as sighting rods, plumb lines, measuring cords, and water levels. However, Amantia raises the possibility that Illyrian engineers possessed surveying traditions far more sophisticated than previously assumed. The city appears too well adapted to its environment to be the result of trial and error alone. Someone understood the landscape in extraordinary detail before construction began. Among the most surprising discoveries at Amantia is its ancient stadium. The structure measures roughly 60 meters in length and was built directly into the hillside. At first glance, it may seem less impressive than larger Greek stadiums such as Olympia, yet its location creates a unique engineering puzzle. Constructing a stadium requires more than simply creating an open space. Engineers must stabilize slopes, control erosion, manage rainwater, prevent structural collapse, create usable seating areas, and maintain level competition surfaces. These challenges become significantly more difficult on mountainous terrain. Modern civil engineering projects often devote extensive resources to slope stabilization and drainage systems. Failure can lead to landslides, subsidence, and structural failure. The stadium at Amantia survived for centuries, yet how ancient builders achieved the necessary stability remains only partially understood. Some archaeologists believe the structure demonstrates a sophisticated understanding of terrain modification and load distribution. If true, it would represent another example of advanced engineering knowledge that left almost no written documentation. No city can survive without water. For Amantia, this may have been the most critical challenge of all. The settlement occupied an elevated location far from major rivers, making a reliable water supply essential. Ancient cities across the Mediterranean developed remarkable hydraulic systems. The Romans built aqueducts stretching for tens of kilometers, Greek engineers constructed underground channels and reservoirs, and Persian qanats transported groundwater across deserts. What system sustained Amantia? Archaeologists have identified cisterns and evidence of water management infrastructure, but many details remain uncertain. Researchers suspect that rainwater collection played an important role. Given the region's climate, carefully designed storage systems could capture seasonal rainfall and preserve it throughout drier periods. However, calculations suggest that supporting a significant urban population would require substantial storage capacity and efficient distribution methods. The complete hydraulic network has never been fully reconstructed. Without understanding the water system, it is difficult to explain how the city maintained long-term occupation. The survival of Amantia suggests the existence of engineering solutions that remain only partially visible in the archaeological record. Perhaps the most controversial mystery concerns the identity of the people responsible for these achievements. Amantia existed within a cultural frontier between Illyrian and Greek worlds. Excavations have produced inscriptions written in Greek, coins that demonstrate economic sophistication, religious structures that reveal Mediterranean influences, and architectural features resembling both local and Hellenistic traditions. This mixture creates a difficult question. Did Greek engineers introduce the technologies visible at Amantia, or did local Illyrian builders develop many of these capabilities independently? The answer matters because it affects how historians interpret technological development across the Balkans. For generations, ancient Illyrian societies were often portrayed as less technologically advanced than their Greek neighbours. Amantia challenges that assumption. Its walls, urban planning, public architecture, and engineering achievements suggest a society capable of executing highly complex projects. yet the precise origins of that expertise remain unclear. Situated on a steep hill in Veliko Tarnovo, central Bulgaria, and almost entirely encircled by a bend of the Yantra River, Zarovets served as the capital fortress of the Second Bulgarian Empire between the 12th and 14th centuries. Archaeological investigations began in the late 19th century and intensified throughout the 20th century, revealing the remains of royal palaces, churches, defensive walls, towers, roads, reservoirs, and hundreds of residential structures. Yet, despite more than a century of research, Zarovets continues to raise questions about the engineering knowledge that made such a complex fortress city possible. One of the first mysteries involves the choice of location itself. Zarovets occupies a hill approximately 206 meters above sea level and covers around 12 hectares. At first glance, the position appears ideal for defense. However, transforming a steep rocky hill into the administrative and political center of an empire was an enormous engineering challenge. Medieval builders had to create stable foundations for hundreds of buildings while working on uneven bedrock. Modern engineers use surveying instruments, laser scanners, and computer models to evaluate terrain before construction. The builders of Zarovets possessed none of these technologies, yet they successfully organized a densely populated urban center on one of the most difficult landscapes imaginable. Excavations have revealed evidence of extensive leveling operations across the hill. Large quantities of stone were removed, retaining structures were constructed, and artificial terraces were created to support buildings. The remarkable precision of these modifications suggests that the builders possessed a sophisticated understanding of terrain management. What remains unclear is how they measured elevations and slopes accurately enough to coordinate construction on such a scale. Similar questions surround other ancient engineering achievements such as Machu Picchu in Peru, where builders transformed a steep mountain ridge into a functioning city. In both cases, the final result demonstrates a level of planning that appears far beyond what many people associate with medieval construction. The second mystery concerns the defensive walls. Zarovets was protected by walls stretching roughly 1,100 meters around the hill. Some sections reached heights of 10 meters or more, reinforced by towers strategically positioned along vulnerable approaches. These fortifications survived centuries of warfare, earthquakes, weathering, and neglect. Modern structural analysis has shown that many ancient walls achieved their strength not simply through mass, but through carefully engineered internal construction. At Zarovets, builders used an outer facing of stone combined with an inner core filled with rubble and mortar. This technique distributed stress throughout the structure rather than concentrating it in a single layer. Modern engineers employ similar principles in composite construction systems. What researchers still debate is the exact composition of the mortar used within the walls. Samples reveal a surprisingly durable material capable of resisting environmental degradation for hundreds of years. Similar mysteries surround Roman concrete, which continues to attract scientific attention because of its extraordinary longevity. While Zarovets did not employ Roman concrete, its builders clearly understood material properties at a level that remains difficult to reconstruct. The third mystery involves water management. Every fortress faces the same fundamental problem: survival during siege. Food can be stored, but water is far more difficult to secure. Zarovets stood high above the Yantra River, making direct access dangerous during wartime. Archaeologists have discovered reservoirs, wells, cisterns, drainage systems, and evidence of sophisticated water infrastructure throughout the fortress. The challenge becomes even more impressive when considering population estimates. Historians believe that several thousand people may have lived within the fortified area and surrounding districts during the empire's peak. Even a conservative estimate of 3 litres of water per person per day would require thousands of litres daily. Maintaining such supplies during a prolonged siege would have demanded careful planning. Researchers remain uncertain whether the fortress relied primarily on rainwater collection, underground springs, deep wells, or a combination of all 3. Geological studies suggest that natural water sources may exist beneath portions of the hill. If medieval engineers successfully identified and exploited these sources, they demonstrated practical knowledge of hydrogeology centuries before the development of modern geological science. Similar mysteries appear at Masada in Israel, where ancient builders created systems capable of supporting life in an arid environment through advanced water storage technologies. Another unresolved puzzle concerns urban planning. Archaeological excavations have identified more than 400 structures inside the fortress. These included residences, workshops, churches, administrative buildings, storage facilities, and military installations. The arrangement was not random. Roads connected key sectors, important buildings occupied elevated positions, and defensive considerations influenced overall organization. Creating such a layout required more than architectural skill. It demanded coordination, logistics, and long-term planning. Modern urban planners use maps, engineering surveys, and population models. The designers of Zarovets achieved comparable organizational results without any surviving technical documentation. Historians know that medieval Bulgarian rulers employed skilled builders and administrators, but the precise methods used to coordinate construction remain largely unknown. One of the most fascinating mysteries centers on the royal palace complex. Excavations have revealed a substantial administrative and residential center, occupying one of the most secure locations within the fortress. The palace included reception halls, defensive structures, residential quarters, and service areas. Researchers studying the ruins have identified evidence suggesting careful environmental design. Certain spaces appear optimized for airflow, temperature regulation, and natural lighting. Today, architects refer to such techniques as passive climate control. Similar principles can be observed in structures ranging from Byzantine palaces to Islamic architecture in southern Spain. Whether the builders consciously applied scientific principles or relied on accumulated practical experience remains uncertain. Either way, the results indicate a sophisticated understanding of how architecture could improve comfort and functionality. The next mystery involves hidden infrastructure. Local legends have long described secret tunnels beneath Zarovets. Stories speak of underground passages connecting strategic points, escape routes leading beyond the walls, and concealed access to water sources. While folklore often exaggerates reality, archaeological investigations have identified subterranean features in several locations. Geophysical surveys have detected anomalies beneath portions of the hill that may represent buried structures. However, the full extent of any underground network remains unknown. Excavation is difficult because many areas lie beneath reconstructed sections of the fortress or modern infrastructure. If extensive tunnels once existed, they would have represented a major engineering achievement. Excavating stable underground passages through rock requires knowledge of structural stability, drainage, and ventilation. Ancient engineers from Cappadocia in Turkey created entire underground cities using such techniques. Whether Zarovets contained anything comparable remains one of the site's enduring mysteries. Military engineering presents another unanswered question. The fortress successfully defended the capital of the Second Bulgarian Empire for more than 2 centuries. Its walls, towers, gates, and natural defenses worked together as a unified system. Modern military historians often emphasize how effectively the fortress exploited topography. Attackers faced steep slopes, limited approaches, and multiple defensive layers before reaching critical areas. Such effectiveness was not accidental. Someone had to analyze the terrain, identify vulnerabilities, and integrate natural and artificial defenses into a coherent strategy. Yet no medieval engineering manuals survived to explain how these calculations were performed. Similar mysteries surround many ancient fortifications, from Celtic hill forts to Byzantine strongholds. The structures survive, but the technical knowledge behind their design has largely vanished. Perhaps the greatest mystery concerns the craftsmen themselves. Zarovets was not built by a single ruler or generation. Construction, expansion, maintenance, and reconstruction occurred over centuries. Thousands of workers, masons, surveyors, carpenters, blacksmiths, and engineers contributed to the fortress. These specialists possessed knowledge that was rarely written down. Skills were transmitted through apprenticeship and experience. When political systems collapsed, much of that expertise disappeared with them. The fall of Veliko Tarnovo to the Ottoman Empire in 1393 marked the end of Zarovets as an imperial centre. Although many structures survived, the technical traditions behind them gradually faded from history. In southern Albania, approximately 14 kilometers east of the modern city of Gjirokastra, lie the ruins of Antigoniea, an ancient city founded around 295 BC by King Pyrrhus of Epirus and named after his wife, Antigone. Although local ruins had been known for centuries, systematic archaeological excavations began during the 20th century and revealed one of the most sophisticated urban centres of the Hellenistic world. Yet despite decades of research, Antigoniea continues to raise questions that modern archaeology cannot fully answer. The first mystery begins with the city itself. Antigoniea covers roughly 35 hectares and was constructed on a mountainous ridge overlooking the Drino Valley. Unlike settlements that evolved gradually over centuries, Antigoniea appears to have been planned from the beginning according to a carefully designed urban blueprint. The streets followed a grid pattern associated with the Hippodamian planning system, one of the most advanced forms of urban design in the ancient Mediterranean. Similar layouts can be found at Priene in modern Turkey and Alexandria in Egypt. However, Antigoniea faced a challenge those cities did not. The terrain was far from flat. Modern topographic studies show significant elevation changes throughout the site. Constructing straight streets, aligned building blocks, drainage systems, and defensive structures on uneven ground required extensive surveying. Today, engineers rely on laser levels, GPS systems, drones, and digital terrain models. The builders of Antigoniea had none of these tools. Instead, they relied on ropes, measuring rods, sighting instruments, geometry, and practical experience. Archaeologists still debate how Hellenistic surveyors achieved such precision across an entire city. No technical manuals describing the actual construction process have survived. The finished city remains, but much of the knowledge used to create it disappeared long ago. The most visible evidence of Antigonea's engineering capability is its defensive system. The city was surrounded by walls extending for several kilometers, many sections of which still survive today. Massive limestone blocks were quarried, transported, shaped, and assembled into fortifications designed to protect the city from invasion. The logistics involved were extraordinary. Researchers estimate that thousands of tons of stone were required, and even a single limestone block could weigh several tons. Without cranes, trucks, or steel machinery, every piece had to be extracted and moved using ancient methods. The challenge becomes even more impressive when considering the location. Transporting stone across flat terrain is difficult enough, but transporting it uphill onto a ridge requires careful planning, coordinated labour, and sophisticated engineering. Similar construction problems can be observed at the ancient fortifications of Mycenae, Pergamon, and Rhodes. Yet unlike some of those sites, Antigoniera has left behind very little evidence explaining exactly how its builders organised the process. The walls reveal the result, but the methods remain largely unknown. One of the least discussed but most intriguing mysteries involves mathematics. Every planned city depends on measurement. Road widths, building plots, public spaces, drainage gradients, and defensive structures must all fit together within a coherent design. Small errors become larger over distance, and a surveying mistake of only a few centimetres can create major alignment problems hundreds of metres later. Modern engineers solve such problems using advanced instruments, while ancient engineers relied on geometry. The Greek world produced remarkable mathematicians such as Euclid and Archimedes, and their theoretical knowledge is well documented. What remains uncertain is how extensively such mathematical principles were applied by practical builders working on large-scale projects like Antigoniera. Some researchers believe Hellenistic engineers possess surveying techniques far more advanced than surviving evidence suggests. Others argue that generations of specialized craftsmen transmitted knowledge through apprenticeship rather than written documentation. If true, much of that expertise may have vanished forever when the city was destroyed. No ancient city could survive without water, and this presents a problem. Antigoniera was not located directly beside a major river. Instead, it occupied a strategic elevated position, chosen primarily for defense. The inhabitants therefore needed systems capable of collecting, storing, distributing, and conserving water throughout the year. Archaeological investigations have identified drainage channels, cisterns, and hydraulic features within the city. These structures demonstrate a significant understanding of water management. Yet many questions remain unanswered. How much water could the system store? How did engineers prevent contamination? How were seasonal droughts managed? How efficiently could water be distributed during a siege? Ancient Greek and Roman hydraulic systems continue to astonish modern researchers. The aqueducts of Rome transported hundreds of thousands of cubic meters of water daily, while the underground qanats of Persia extended for tens of kilometers beneath deserts. Antigoniera operated on a smaller scale, but its mountain setting created engineering challenges of its own. The complete design of the city's hydraulic network remains unknown. One of the most surprising aspects of Antigoniera is how quickly it appeared. Unlike cities that evolved gradually over centuries, Antigoniera was founded as part of a deliberate political project under Pyrrhus. The king needed a functioning urban centre, capable of supporting administration, trade, defence, and regional control. This suggests that major portions of the city were completed within a relatively short period. Such rapid construction raises important questions. How many workers participated? How was food supplied to the workforce? Where were construction materials processed? How were multiple building projects coordinated simultaneously? Modern project managers use schedules, digital models, logistics software, and communication networks to coordinate large developments. Ancient builders accomplished similar feats without any of these technologies. The administrative systems that made Antigoniera possible have almost completely vanished from the historical record. Excavations have uncovered evidence of workshops, production areas, ceramics, and various forms of economic activity. These discoveries reveal that Antigoniera was not merely a military stronghold, but a functioning urban economy. Ancient industries required fuel, raw materials, transportation networks, specialized labor, and quality control. Pottery kilns, metalworking operations, and construction workshops all depended upon technical knowledge accumulated over generations. Yet the people responsible for these industries remain largely invisible. Archaeologists can analyze finished products using microscopes, chemical testing, and material science. They can identify mineral compositions and manufacturing traces. However, reconstructing the complete production process remains far more difficult. The artifacts survived, but the expertise often did not. Situated in western Armenia near the modern town of Agarak in Aragatsutn province, this remarkable archaeological complex was first identified during 20th century investigations and later excavated extensively by Armenian researchers. Spanning nearly 200 hectares, it is one of the largest archaeological sites in the South Caucasus. What makes it especially unusual is that much of the complex was not constructed from stacked stone blocks. Instead, ancient builders carved and reshaped vast areas of natural volcanic bedrock, creating an immense engineered landscape. Thousands of years later, archaeologists still cannot fully explain how or why many of these features were made. The first mystery begins with the scale of the rock-cut landscape itself. Unlike most Bronze Age settlements, Agarak contains hundreds of carved features directly cut into solid basalt. Researchers have documented platforms, stairways, channels, basins, pits, terraces, and geometric formations extending across large portions of the hill. Some structures appear ceremonial, while others resemble engineering works. Together they create a landscape that looks less like a settlement and more like a gigantic stone blueprint. The challenge is understanding the purpose behind this effort. Creating such features required enormous amounts of labour. Basalt is significantly harder than limestone, registering approximately 6 on the Mohs hardness scale compared with limestone's average hardness of around 3. Ancient workers therefore faced a material roughly twice as hard as the stone used in many famous monuments of the ancient world. Yet they reshaped vast areas of bedrock centuries before advanced iron tools became widespread in the region. The mystery is not simply how the stone was cut, it is why so much effort was invested into modifying an entire landscape. Some researchers interpret the site as a sacred complex, while others suggest it functioned as a regional ceremonial centre connected to agricultural cycles, political authority, or astronomical observations. No single explanation accounts for all the carved features found across the site. The second mystery involves the technology used to shape the volcanic rock. Many of the oldest features at Agarak date to the early and Middle Bronze Age, roughly between 3000 and 1500 BC. During this period, metallurgy existed but remained limited compared with later Iron Age technologies. Archaeologists know that copper and bronze tools were available. However, experimental archaeology has repeatedly demonstrated the difficulty of carving large quantities of basalt using Bronze Age equipment. Tool marks preserved on some surfaces indicate systematic planning rather than random modification. The cuts often follow deliberate lines. Platforms were levelled with surprising consistency, and certain channels maintain controlled dimensions over considerable distances. These observations raise difficult questions. Were specialised stoneworking techniques employed that are no longer understood? Did workers combine fire-setting methods with hammerstones and metal tools? How many generations were required to create the landscape visible today? The absence of written records means the technology behind the project remains largely invisible. This problem mirrors mysteries encountered elsewhere in the ancient world. Researchers studying the quarries of ancient Egypt continue debating aspects of granite extraction at Aswan, while specialists examining the megalithic builders of Malta face similar questions regarding large-scale stone modification. Agarak belongs to this same category of archaeological puzzles where the evidence for achievement survives, but the technical instructions have disappeared. The third mystery centers on the strange geometric carvings spread throughout the site. Across the bedrock are numerous basins, depressions, channels, and carved forms whose functions remain uncertain. Some resemble ritual installations, while others look surprisingly practical. One interpretation suggests that many of these features were designed for ceremonies involving liquids. The channels could have directed water, wine, oil, or sacrificial offerings, and similar ritual systems have been documented in several Bronze Age cultures throughout the Near East. However, not every structure fits this explanation. Certain arrangements appear excessively large or unusually organized if their sole purpose was ritual activity. In some places, multiple carved elements connect together in patterns that resemble engineered systems rather than isolated ceremonial installations. This has led some researchers to propose alternative interpretations involving administration, agriculture, resource management, or community gatherings. Yet definitive evidence remains elusive. The fourth mystery concerns hydraulic engineering. Water was one of the most valuable resources in the ancient world. Civilizations from Mesopotamia to the Indus Valley developed increasingly sophisticated methods of controlling it. At Agarak, archaeologists have identified numerous channels and carved depressions that may have been involved in water management. If this interpretation is correct, the implications are significant. Hydraulic systems require more than simple excavation. Builders must understand gradients, flow rates, erosion, storage capacity, and seasonal variation. Even a small error in slope can prevent a channel from functioning properly. Modern surveys suggest that some carved features were positioned with remarkable awareness of the surrounding terrain. The possibility that Bronze Age engineers intentionally integrated natural topography into a coordinated water management system remains one of the most intriguing aspects of the site. Comparable achievements are known from the ancient kingdom of Urartu, whose engineers later constructed canals stretching dozens of kilometers across Armenia. Yet many features at Agarak predate those famous hydraulic projects by centuries. Whether the channels serve practical engineering purposes, ritual functions, or both remains unresolved. The fifth mystery involves astronomy. Ancient societies frequently linked architecture with the sky. Monuments such as Stonehenge in Britain, Nabta Playa in Egypt, and Chanquillo in Peru demonstrate that prehistoric peoples often incorporated celestial observations into construction projects. At Agarak, some researchers have suggested that certain carved platforms and elevated locations may have been used for observing seasonal events. The site occupies a strategically elevated position overlooking parts of the surrounding landscape. From these vantage points, important solar events such as solstices and equinoxes would have been visible. Supporters of the astronomical hypothesis argue that repeated patterns and orientations could reflect intentional alignments, while critics point out that the evidence remains insufficient. Unlike Stonehenge, where alignments can be measured directly, Agarak lacks clear architectural markers proving astronomical intent. Many supposed alignments could simply result from practical construction decisions or natural geography. As a result, the astronomical interpretation remains one of the most debated aspects of the site. The sixth mystery is perhaps the most surprising. Agarak was not occupied for a brief period before being abandoned. Archaeological evidence indicates repeated use across multiple eras. Bronze Age communities utilized the site, later Iron Age populations returned, and elements of the complex continued attracting attention during the period of the Kingdom of Urartu. This continuity spans well over 1,000 years. Very few locations maintain cultural importance for such an extended period, unless they possess exceptional religious, political, strategic, or economic significance. Yet the reason Agarak retained its importance remains unclear. Did later civilizations understand the original purpose of the carvings, or were they inheriting a sacred landscape whose meaning had already begun to fade? This possibility introduces another layer of mystery. The site may have become ancient even to the people who later occupied it. What do you think was the true purpose of Agarak's mysterious rock-cut landscape? A sacred ceremonial center, an advanced hydraulic system, or evidence of lost engineering knowledge? Share your thoughts in the comments below. Zgurdesh, an ancient city located on a hill about 15 kilometers south of modern Kruja, remains one of Albania's most intriguing archaeological sites. Overlooking key routes that once linked the Adriatic coast with the interior Balkans, the settlement occupied a strategically important position. Archaeological investigations that began in the early 20th century uncovered the remains of a large fortified city dating mainly from the 4th to the 2nd centuries BC. Many scholars believe the site may have been Albanopolis, the principal centre of the Illyrian tribe known as the Albani, mentioned by the geographer Ptolemy in the 2nd century AD. Despite more than a century of research, the ruins continue to pose challenging questions about engineering, urban planning, logistics, and technological knowledge that are still not fully understood. The first mystery begins with the location itself. Ancient builders selected a hill rising more than 300 meters above sea level, commanding extensive views across the surrounding valleys. Modern military analysts recognize the strategic advantages immediately. From the summit, observers could monitor movement over a vast area while remaining protected by steep slopes. What remains unclear is how Illyrian surveyors identified and evaluated such an optimal position without maps, aerial photography, satellites, or modern surveying equipment. Today, engineers use GPS systems capable of centimeter-level accuracy and digital terrain models generated by satellites. The builders of Zgurdesh possessed none of these technologies, yet they chose a position that maximized visibility, defense, and access to trade routes simultaneously. The methods they used to survey the landscape have disappeared from history. The second mystery concerns the massive fortification system surrounding the settlement. Archaeologists have documented defensive walls extending approximately 1,400 meters around the hilltop. Some sections were constructed using large limestone blocks fitted together with remarkable precision. The fortifications protected an urban area estimated at around 20 hectares, making Zgurdesh one of the most significant Illyrian centers discovered in Albania. The engineering challenge was enormous. Thousands of tons of stone had to be quarried, transported uphill, shaped and assembled into stable defensive structures capable of resisting both attack and natural weathering. Comparisons with other ancient fortifications reveal the scale of the achievement. The famous walls of Mycenae in Greece employed Cyclopean masonry using enormous stone blocks. Similar techniques appear in parts of Zgurdesh, although on a smaller scale. The question is not whether the walls could be built, but how the builders organized the labor and logistics required. No written records survive describing construction procedures, workforce management, or engineering calculations. The walls stand as evidence of technical expertise, while the knowledge behind them remains largely invisible. A third mystery involves stone transportation technology. Many blocks incorporated into the defences weigh several tons. Modern engineers would typically rely on cranes, trucks, steel cables, and hydraulic systems to move such materials efficiently. Ancient Illyrian builders had none of these advantages. Researchers have proposed the use of wooden rollers, sledges, earthen ramps, and large coordinated labour teams. Experimental archaeology has demonstrated that prehistoric societies could move heavy stones using surprisingly simple tools. However, no direct evidence reveals exactly which techniques were employed at Zgurdesh. The problem becomes even more intriguing when considering the terrain. Transporting multi-ton stones across relatively flat ground is difficult enough. Moving them uphill to a fortified settlement presents an entirely different engineering challenge. Every block visible in the walls represents a logistical operation that remains only partially understood. The absence of construction records leaves archaeologists reconstructing possibilities rather than certainties. The fourth mystery centers on urban planning. Excavations indicate that Zgurdesh was not merely a military fortress. The settlement contained residential districts, public spaces, streets, storage facilities, and structures associated with administration and trade. This suggests a sophisticated urban environment rather than a simple defensive outpost. Modern urban planners analyze traffic flow, population density, water availability, and defensive requirements before designing a city. Ancient planners faced similar challenges without mathematical modeling software or detailed engineering manuals. Yet the layout of Zgurdesh demonstrates clear organization. Buildings occupied carefully selected terraces, circulation routes connected different sectors of the settlement, and defensive features integrated with the natural landscape. One unanswered question is whether the city developed gradually over generations or followed a master plan established from the beginning. Some archaeological evidence suggests deliberate planning, while other features indicate organic growth. Determining where planning ends and adaptation begins remains one of the site's most difficult puzzles. The fifth mystery concerns water management. Every ancient city depended on reliable access to water. A settlement occupying a hilltop fortress faced particular challenges because rivers and springs were usually located below the defended area. Archaeologists have identified evidence suggesting systems for collecting and storing water, but the full hydraulic network remains uncertain. This issue has significant engineering implications. An urban population could not survive prolonged occupation or military siege without dependable water supplies. Ancient civilizations from Rome to Persia developed sophisticated hydraulic technologies, including aqueducts, cisterns, underground channels, and reservoirs. The inhabitants of Zgurdesh must have solved similar problems, yet much of the infrastructure has either vanished or remains undiscovered. Modern researchers use ground-penetrating radar, geophysical surveys, and digital terrain analysis to search for hidden features. Even with these technologies, many aspects of the settlement's water management system remain unknown. The possibility that portions of the hydraulic network are still buried beneath the site continues to attract scientific interest. The sixth mystery involves trade and economic organization. Archaeological discoveries indicate contact between Zgurdesh and the wider Mediterranean world. Imported pottery, coins, and other artifacts reveal participation in regional exchange networks, extending far beyond the settlement itself. Trade requires infrastructure. Goods must be transported, stored, recorded, protected, and distributed. Such activities imply roads, warehouses, administrative systems, and specialized labor. Yet only fragments of this economic machinery survive. Researchers can identify evidence of trade but cannot fully reconstruct the mechanisms that sustained it. The challenge resembles attempting to understand a modern city after every computer, document, and administrative building has disappeared. The surviving artifacts demonstrate that commerce occurred. The systems that made commerce possible remain largely hidden. Another fascinating mystery concerns construction durability. More than 2,000 years after the city's decline, significant portions of the walls remain standing. This longevity reflects engineering decisions that proved remarkably effective. builders selected suitable stone, understood load distribution, and adapted structures to the local geology. Scientists studying ancient construction frequently encounter similar questions elsewhere. Roman concrete continues to attract research because some formulations have survived for millennia. Inca masonry demonstrates extraordinary resistance to earthquakes. The builders of Zgurdesh may not have possessed identical technologies, but they clearly understood principles of stability and durability that deserve greater investigation. Perched atop a volcanic basalt plateau in present-day Hesse, Germany, Dornberg Oppidum was an Iron Age stronghold that commanded sweeping views of the surrounding landscape from nearly 400 meters above sea level. Archaeologists believe Celtic communities occupied the site between the 6th and 1st centuries BC. Unlike many ancient cities that left written records, Dornberg left behind only walls, artifacts, and unanswered questions. What remains suggests that its builders possessed engineering knowledge far more sophisticated than many people imagine. The site was first recognized through archaeological investigations of the Dornberg Plateau, where massive defensive earthworks and stone fortifications reveal the existence of a large Celtic oppidum. Excavations uncovered coins, iron tools, glass ornaments, pottery, and evidence of long-distance trade. Yet the discoveries raised more questions than answers. How did Iron Age engineers transform a volcanic mountaintop into a fortified urban centre? How did they manage water, construction, and logistics in such a challenging environment? And why did so much of their technical knowledge disappear? The first mystery involves the remarkable selection of the location itself. Modern military engineers understand the importance of terrain. High ground provides visibility, defensive advantages, and control over movement across a region. The builders of Dornberg appear to understand these principles more than 2,000 years before the development of modern military science. The plateau is protected naturally by steep slopes and volcanic rock formations. However, the Celts did not simply rely on nature. They constructed additional defensive walls exactly where attackers would have had the greatest chance of reaching the settlement. Archaeological surveys indicate that sections of the fortification system stretched hundreds of meters and were positioned with impressive strategic efficiency. This raises a significant question. How did Celtic surveyors determine the optimal placement of these defences without maps, aerial views, or modern measuring instruments? Today, engineers use digital terrain models, satellite imagery, and computer simulations to identify defensive weak points. The builders of Dornberg possessed none of these tools, yet the fortifications demonstrate an understanding of topography comparable to principles still taught in military academies. Researchers can identify the results of that knowledge, but the methods used to obtain it remain largely unknown. The second mystery concerns construction technology. Dornberg was built on a basalt plateau formed by ancient volcanic activity. Basalt is one of the hardest common volcanic rocks, and even with modern steel equipment, quarrying and shaping basalt requires significant effort. The Celts, however, worked primarily with iron tools. This presents a logistical puzzle. Thousands of tons of stone were moved, positioned, and incorporated into defensive structures. Every block had to be extracted, transported, and assembled without cranes, engines, or mechanized equipment. Similar challenges can be seen at famous sites such as the Great Pyramid of Giza, where researchers continue debating construction methods after centuries of study. At Dornberg, the problem is equally intriguing. How were large quantities of basalt transported across uneven terrain? How many workers were required? What organizational system coordinated such projects? Experimental archaeology suggests that moving a single stone block weighing several hundred kilograms could require dozens of people using ropes, sledges, and wooden rollers. Multiply that process thousands of times, and the scale of the undertaking becomes extraordinary. Yet no written records survive to explain how the builders managed it. The third mystery involves urban planning. Evidence recovered from the site indicates that Dornberg was more than a military fortress. Archaeologists discovered coins, jewelry, tools, and imported goods. These finds suggest that the settlement participated in regional trade networks and may have functioned as an important economic centre. If that interpretation is correct, then hundreds or perhaps thousands of people may have occupied the plateau during its peak. This creates a difficult question. How did such a population survive on top of a volcanic hill? Any permanent settlement requires access to water. An adult typically needs several litres of water per day simply for survival, and a community of 1,000 people could require thousands of litres daily. Yet archaeologists have found limited evidence for large reservoirs or sophisticated water infrastructure. This absence is puzzling. Either important hydraulic systems remain undiscovered, or the inhabitants developed methods of water collection and storage that left little archaeological trace. Similar debates surround several other Celtic oppida across Europe, where populations appear larger than the visible water infrastructure would seem to support. The fourth mystery concerns trade and communication. Excavations revealed objects that originated far beyond the immediate region. Glass ornaments, imported materials, and coinage indicate participation in extensive commercial networks. This is particularly surprising because Dornberg occupies a relatively isolated volcanic plateau. The movement of goods across Iron Age Europe required roads, routes, intermediaries, and logistical coordination. Modern transportation networks rely on maps, infrastructure, and administrative systems. Yet centuries before the Roman Empire constructed its famous roads, Celtic societies were already moving valuable materials across hundreds of kilometers. Researchers still debate the complexity of these networks. Some believe that Celtic Europe maintained interconnected trade corridors linking settlements across much of the continent. Others argue that trade occurred through numerous local exchanges rather than centralized systems. Whatever the explanation, the artifacts found at Dornberg reveal a level of economic integration that many people would not associate with Iron Age societies. The fifth mystery may be the strangest of all. Near Dornberg lies a geological phenomenon known as eternal ice. Within cracks and cavities in the basalt, cold air circulation creates conditions that allow ice to persist even during warmer months. Scientists explain the phenomenon through thermodynamics and airflow within the volcanic rock. Cold winter air becomes trapped underground and continues influencing temperatures long after winter has ended. The scientific explanation is well understood today. What remains unknown is whether the ancient inhabitants understood and exploited the phenomenon. If they did, the implications are fascinating. Natural refrigeration could have been used for food preservation, storage of valuable goods, or ritual activities. Similar uses of natural cooling systems have been documented in other parts of the world, where ancient communities learned to exploit local geological conditions long before the invention of mechanical refrigeration. No direct evidence confirms such usage at Dornberg, but the possibility remains one of the site's most intriguing unanswered questions. Which mystery fascinates you most about Dornberg Oppidum? Let us know your thoughts in the comments below.